right, great. All right, well then let's jump in and get the show on the road. So first, let me apologize for the delay in getting this meeting scheduled. Were some inevitable complications with the administration transition, as there always are. So thanks for your patience as we found today, and apologize for the abbreviated meeting, but a lot of stuff is going on. I was saying before we started to Christine that I was really hoping I could say I'm really looking forward to see you in person at our next meeting, but I think that's unlikely right now. I am really hoping that our first calendar year 2022 meeting will be in person. But I'm also reminded of the old saying about Frisbee tosses that one should never preface the description with anything more informative than watch this. So we will hope for the best. So I'm glad you're all here. It's great to see all your faces. Unless anyone has any initial questions or comments, I'll hand the floor over to Steve Binkley to give us the view from DC. So,
before that, did you want to allow the new members to introduce
themselves?
Yes,
thank you. Apologies. So we do have new members, and getting them through the process was also part of the reason for delaying the meeting a bit. So I'll thank you, Christine, for reminding me of that, and apologies for not going there immediately. So those of you who are new members of the committee, maybe just, I think we all know you, but it's always good for the audience and have a little bit of introduction. So chime in one by one and introduce yourselves, and we'll go from there.
Hi, it's Roscoe. I'm back.
Welcome back, Roscoe.
Boston University.
So I'm Bruce Hendrickson, Associate Director for Computing at Livermore Lab. I think you all know me.
Welcome, Bruce. Thanks for all the work on the history report, and thanks to Roscoe for all the work on the post ECP report as well.
I'm Jill Meserov, and I'm a professor of medicine at UC San Diego, and I also serve as Associate Vice Chancellor for health sciences, computational science, really. It's kind of nice to see all these people who I interacted with much more frequently in a previous life, but it looks like what goes around comes around, or something like that. So it's great to see you all.
Well, we're glad to have you, Jill. And yes, I think we all go back a long way in previous lives. So glad to have you here as part of ASCAC.
the last new member is Rick Arthur, and I don't see him connected yet, so he might be having some trouble connecting. But Rick Arthur from GE, we'll let him say hi after the break, or at the break.
All right, thanks for appropriately reminding me of that, Christine. Steve, over to you.
Okay, thanks, Dan. Can you hear me okay?
Yes.
So I'm going to be brief, and I don't have slides. I want to start by thanking the entire ASCAC for your service in this capacity. You know, as I've said many times before, we at headquarters really understand the time commitment that's involved, and it's really important to us, the work that the advisory committees do. And so I want to thank you for the service that you're rendering to the Department of Energy. As you probably know, I'm back in the position of acting director for the Office of Science with a change of the administration. We're waiting for nominees to be confirmed. But then once that happens, I'll go back to my regular day job, which is as the principal deputy director for the overall organization. And the first topic I'd like to take up this afternoon, this morning, depending on where you are, is the status of our political appointees. The new political team is shaping up very nicely. Secretary Granholm has been with us at DOE for several months now and has been quite active articulating the vision of the Biden-Harris administration. Deputy Secretary Turk is also on board, and we've had a number of interactions with him already. He's, because of his previous experience in the international affairs and policy part of DOE, he's very knowledgeable of the department, having returned to the U.S. Just recently from a post with the IAEA in Paris. We have nominees for both the Director of the Office of Science and also for the Undersecretary for Science. The nominee for the Director of the Office of Science is Asmaret Berhe, who is a professor at the University of California, Merced. Jerry Richmond is the nominee to be the Undersecretary for Science. She's a professor in the chemistry department at the University of Oregon, and she's very well known to us in SC because of her years of service on the Basic Energy Sciences Advisory Committee, including being the chair of BSAC. And in breaking news on this, both nominees are scheduled to have their confirmation hearing before the Senate Energy and Natural Resources Committee this coming Tuesday. And so we're looking forward to a successful completion of that step, which is necessary before the vote for their confirmation can be taken up by the full Senate. And then you may have noticed that shortly after the start of the new administration, the DOE applied energy programs were put back under our Undersecretary, and it's now back to being the Undersecretary for Science and Energy, much like it was during the second term of President Obama. This, I think, is really a very good thing to do because it brings the Office of Science programs into closer proximity with the applied energy programs, and is actually very helpful in collaborating with the applied energy programs. We also, in our front office, we have two political appointees on board. The first is Tanya Doss, who is our Chief of Staff, who reports directly to the Director. Tanya received a PhD from the University of California, Santa Barbara in mechanical engineering and was a professional staff member on the House Space Science Committee before coming to DOE in January. And then secondly, Natalie Tham, who is a special assistant. And then the second topic that I'd like to turn to is the status of the budget. The President's budget request for fiscal year 2022 was sent over to the Congress in May, and the top line budget for the Science, Office of Science top line budget number in the request is $7.44 billion, which is an increase of $414 million over fiscal year 2021. That's an increase of 5.89%. And then lastly, the House Energy and Water Development Appropriation Subcommittee marked up the 2022 budget just recently, and their markup is slightly less than the President's request, coming in at $7.32 billion. And, we're anxiously awaiting now the Senate markup, which I think may be out even this week. And Barb will cover the details of the Oscar budget in her talk. And at that point, I would like to stop, and I'd be happy to take any questions.
Thank you, Steve. Are there questions for Steve about budgets or appointees or anything else? Richard?
Yeah, thanks, Dan. I'll fix my mic. Steve, thank you. Can you speak to any changes at the Office of Science in terms of priorities that you see on the horizon from the new appointees?
Yeah, well, there's three areas that they are putting very high priority on, and they're not unfamiliar to the Office of Science. So the first one is clean energy. One of the administration's major goals is net zero by 2050, and the Office of Science has been working, if you look at our overall budget, we have a very significant amount of our research portfolio is focused on clean energy. And in fact, we maintain what we call a clean energy and climate crosscut, and it's out of the $7 billion budget, the amount of research that we fund that's directly related to clean energy and climate is about $2.7 billion. So it's a fairly significant fraction of our overall budget. And so climate is also one that, the climate research, which is really mainly in the biological and environmental research area, has grown quite a bit in the budget request, reflecting the need to do better modeling and simulation and more thorough analyses of climate effects overall. And then the third area that is really very, very high priority for the administration, and coincidentally, it's been very high priority for the Office of Science now for 5 years or so, is diversity, equity, and inclusion. And in the reorganization that Director Chris Fall did with the organization about 1.25 years ago, we established an actual office for diversity, equity, and inclusion. And we're now in the process of staffing that office up. We've been working very hard with the labs for almost 5 years now on diversity plans. And that's I think progressed very nicely. And we're also very much now focused on the diversity, equity, and inclusion for the federal workforce. So I don't see it as a shift away from the priorities that the office has been following, but definitely a resurgence of interest in clean energy and climate. And there'll be what are called Earthshot initiatives. But there's been two identified so far. One has to do with hydrogen, increasing the use of hydrogen for energy production, and then also one that focuses on direct air capture of carbon. So there'll be more of those that are announced over the next several months. And does that address your question?
Yes, Steve, thank you very much.
Thanks, Richard. Any other questions for Steve? All right, not seeing any hands. Thanks, Steve. Appreciate it. Thanks for all you're doing for DOE and a time of transition.
Since we're a little ahead of schedule and I see Rick Arthur has joined us, I thought maybe it'd be a good opportunity for him to introduce himself.
Great, thanks for flagging that. Yes, we were just doing introductions of new members, so please jump in and just say a few words.
All right, I clicked, I guess, the wrong Zoom link before, was in a much smaller meeting. I'm Rick Arthur. I've been working with the DOE for over 10 years now, representing GE and our interests in computational science and engineering, mainly supporting our aviation computational fluid dynamics, materials development, and such. And I'm excited to be joining this group. My background's in computational engineering, and I currently work at the research facility in upstate New York.
Thanks, Rick, and welcome to ASCAC. Appreciate it and look forward to interactions. Anything else, Christine, that I'm forgetting?
No, we're all good.
Okay, good. All right, Steve, as I was saying, thanks to Steve. And we'll move on to Barb, who's going to tell us what's happening in virtual town.
Let me share my slides. Well, and what I want to do is start out with some exciting news for Oscar. As many of you know, I think we've been understaffed for a number of years, and in the last year, we've been able to actually fill a lot of staff positions, at least 3. And I'm going to go in chronological order. I think when we spoke last, we weren't sure. I might have hinted at the fact that we were going to have a facilities division director, but Ben Brown joined us, and well, he actually joined Oscar in 2017 as the ESNet program manager, but as of October 11th, 2020, he became our facilities division director. As I said, he joined us and he was a program manager for ESNet. And before coming to DOE, Ben worked at the Senate as a AAAS fellow. And actually, before coming to Oscar, he actually worked for the deputy director for programs at that time, Pat Damer. Next, in April, we were fortunate to be able to hire Margaret Lentz from the Artificial Intelligence and Technology Office. And she's joining us to actually fill or backfill Laura Bivens' position. Laura, as you remember, was heavily interested in and focused on data and all things data management and tools, and left us to go work at NIH. Margaret, again, as I said, joined us from the Artificial Intelligence Office. She was also a AAAS fellow with NNSA, and she's also a research scientist specializing in medical imaging, neuroscience, and biodefense and image analysis.
Wow.
So we're happy to welcome Margaret on board. And the latest announcement that we have is we now have a facilities or a research division director, Dr. Jaren Sussett, which many of you know because she's led our SIDAC program and more recently the quantum program that we have was officially selected as our Oscar research director. In the past year, she spent a lot of her time, a significant amount of time working across the Office of Science to help us select the 5 quantum centers. And so we're happy to have Jaren ready to focus on the research division. And like, you know, we were able to hire a number of people, but I have to report that we will also have some retirements. Sonia Sachs, who many of you know from her years of being the program manager for computer science, is going to retire. And I think her last day of DOE is tomorrow.
Wow.
She's going to go to work in the private sector. And I especially want to thank Sonia because in the last 5 years, she has been my go-to person. She has stepped up and managed the Argonne Leadership Computing Facility. She's also stepped up and been the program manager for our SBIR and STTR portfolio, ran our ALCC program, and on top of all of that was selected as a co-chair for the NIDR-D High-End Computing Interagency Working Group last fall. So we wish Sonia well, and Sonia also asked me to thank the Oscar community for her opportunity to serve and the privilege to work with many of you. So if we had that water cooler, we could all at break go out and talk to Ben, Margaret, Jaren, and Sonia. So that's my exciting news. And now I'll focus on the budget. Many of you probably read, the appropriations. As you can see, the agreement provided for, identified what we needed to spend on the facilities and not less than $250 million for mathematical, computational, and computer science research, and not less than $10 million for the computational fellowship, and again, up to $40 million for development of AI optimized emerging memory technology for AI specialized hardware to drive national competitiveness. What does that translate into? And when I get to the next table, I not only do I have the enacted appropriations, but I also have a breakout of our request. You can see that last year's enacted appropriation was a little over $1 billion. The president's request for OSCAR was $1.04 billion. There was a slight increase over the enacted appropriations for the applied math and computer science programs. A larger increase for comp partnerships, and I'll come back to that in a minute. But I also want to call your attention to the increase for the Computational Science Graduate Fellowship. And I want to just take this minute to do kudos, to take this opportunity to give kudos to Krell Institute, the CSGS Steering Committee, Selection Committee, and particularly the alumni of the program for their continued involvement in CSGS. I was fortunate this year to observe the Selection Committee meeting and was truly impressed with the efforts they're taking and to make sure that we have a diverse class. And in the over 30 years that I've been involved with the program, this is probably the most diverse class we have. So, and with increased funding that we had from some carryover funds, we were actually fortunate to be able to fund 32 fellows last year. And going back to the budget, there's the increase for quantum information science is to establish quantum test beds. And then I'll come back and talk about some of the other increases in the budget as I go through some of the new initiatives that are in the FY22 program. The first initiative I want to talk about
sorry,
is the
it's been, can I interrupt with a question on the budget?
Sure.
If we could go back, I'm feeling a little like an idiot here, but if you would just look at the applied mathematics line and then the one below it that says artificial intelligence and big data, there's a bunch of negative numbers there. Help me understand how to understand that.
It's not really a negative number. The numbers underneath it are the numbers that are in the applied math programs that are targeted for AI and big data. So they're non-ad. So it's just because we have initiatives in AI and quantum information science, that's how we.
Okay. Thank you for that, because otherwise the arithmetic didn't work.
Well, and the other thing to notice is in exascale, we count some of the Argonne and Oak Ridge leadership computing facilities towards the exascale project, which is why there's a negative number under there. We count all of Argonne and just part of Oak Ridge because Oak Ridge is actually running Summit at this time.
Thank you. I appreciate that.
Okay. And the other thing, just to call attention to it one more time, the reason I have the numbers in red, those aren't negative either. It's because at one time we had the research and evaluation prototypes line underneath the facilities line, and we've moved it up to the research line. When I can get rid of FY20 numbers, then that red line will go away. The other thing to note is starting with the enacted appropriation for FY21, the SBIR numbers, it's not that we're not funding SBIR and STTR anymore. They're all included in the numbers for each of the sub-programs. So we don't have one special line for SBIR anymore.
I see.
I was just going to ask, while we're on the numbers, does anyone else have a question for Barb about the budget?
Barb, question on the SBIR line and its removal. Is the SBIR allocation uniform across all the other lines, or do you see it applied selectively?
No. We apply it uniformly, except that the education programs don't pay SBIR, and any equipment that we have and the capital equipment that we have in the facilities are not taxed for SBIR. And I think there's $5 million across the 3 facilities, and then the 10 to 15 million for CSGS isn't taxed. But the rest of the programs, they're all, and the exascale computing program, because it's considered as a construction project, doesn't pay SBIR and STTR.
Thank you.
Okay.
Any other questions? All right, sorry, Barb.
Well, there'll be ample opportunity to ask other questions as I go through this. So I just want to highlight some of the initiatives that we talked about or that were highlighted in our budget narrative. The first one is the Biopreparedness Research Virtual Environment, or BRAVE initiative, and Oscar is partnering with Basic Energy Sciences and Biological and Environmental Research on this. And it's, in a sense, is taking off where we left, if you remember us talking last year about the National Virtual Biology Laboratory that the 17 labs stood up to support the COVID-19 research. This is to actually extend that work through the 3 programs. So what we want to do is develop a virtual platform to rapidly mobilize DOE's bioscience R&D assets in response to national crises. We'll provide a distributed DOE laboratory research teams with collaborative frameworks and rapid access to Oscar's high-performance computing facilities. We'll work collaboratively on design, build, test, and learn workflows, and support DOE's next generation analytical technology user facility resources and national preparedness. Certainly Oscar in this, within the BRAVE initiative, is interested in taking some of the lessons learned that we learned in our participation in the national COVID-19 HPC consortium with cloud vendors and other agencies. And we want to actually understand the simulation and modeling needs of the SC programs in this area and other agencies. Of course, data management and curation needs, because that was one of the lessons that we definitely took away from the COVID-19 consortium, is we have to have a way to be able to share data and to identify and bridge gaps necessary for DOE to provide the resources on short notice. And to give you more background about BRAVE, later on in this afternoon, Michelle Buchanan is going to talk about the National Virtual Biology Laboratory that we stood up during COVID. So if I go, there was a question to Steve about other initiatives, and Steve talked about the work that we're doing in diversity, equity, and inclusion. And another initiative that Oscar is supporting, and in fact, all of the SC programs are supporting, is the Reaching a New Energy Sciences Workforce, or RENEW. And we're currently using FY21 to do outreach and listening tours to work with minority serving institutions, professionals, societies, and underserved representatives from other communities to gain an understanding of the challenges they have about coming in and working with DOE at the laboratories, applying for our grants and fellowship. And we want to develop evidence-based solutions. So we're currently discussing this within the program's offices in the Office of Science. And I can tell you, based on my experience with CSGF, certainly as we go forward in this, we're really excited to work and expand our communities in applied math, computer science, and especially computational science. So hopefully we'll hear more. You'll hear more about this in coming ASCAC meetings. The integrated computational data infrastructure is not a new initiative this year. And if I can circle back about to BRAVE and RENEW, the funding for BRAVE is included in the computational partnerships line, and the funding for RENEW, which Oscar is targeted at $5 million, is in the research and evaluation line, the same place that CSGF is. Integrated computational and data infrastructure flows across the applied math, computer science, computational partnerships, and now a facilities line. And that is our initiative to provide an enriched discovery environment that will connect our facilities to the other Office of Science user facility. And I have talked about this before, but I showed this slide because I want to talk, I want to put it in context when I talk about pure data assets and the scientific data facility that was also mentioned in our budget. And let me start with the scientific data facility. People like Roscoe will recognize this, that the idea for it came out of the 2013 ASCAC response to the facilities charge. Back then, they suggested that we needed a virtual data facility. As a first step in doing that, we proposed to actually design a high-performance data facility from the ground up that will focus on data handling, scientific computing, workflow management, and more importantly, high-performance real-time and data processing, because what we're hearing from the scientific user facilities more and more is they want to do real-time processing on our HPCs. So we need to be able to provide tools for simulating and managing scientific workflows. And more importantly, we want this facility to be able to integrate edge computing at remote sites to provide real-time access to computing resources that are architecturally diverse than other ASCAC facilities. And of course, they need to integrate with ASCAC facilities. And as the budget noted, we ideally, to provide some graphic diversity, we hope to locate this facility someplace on the East Coast. And again, as we move into real-time data processing, I have to make sure that I have tools and resources and computing available, almost 24 hours a day, 7 days a week. So I have to account for time that other facilities might have been down for maintenance or upgrades. So that's why we're proposing a new facility. I mentioned the pure data resource. This is a recognition. I have to give kudos to Laura Biven, who with her data working group here in the Office of Science started this, recognized that data is the third pillar of the DOE enterprise, along with our scientific user facilities and along with our research funding. We produce a lot of data that is usable by the community, so we wanted to make sure that we put it in a form that it's truly reusable and make it publicly available. And so the pure data resource designation on our data highlights and improves the stewardship of our SC supported community data efforts with the strategic impact on the SC mission. And the first data and data repositories, so designated as pure data resources, include the data coming out of the Joint Genome Institute, the National Nuclear Data Center, the Particle Data Group, the Materials Project, the ARM data set, the Atmospheric Radiation Measurement, and KBase, which is System Biology knowledge base. So again, this integrated computational and data infrastructure initiative that we propose is connecting all of this together to make it easier for people to use SC facilities. So let me now, that was what we proposed in our FY22 budget, presidential budget request. And as Steve said, we do have an appropriation, a House markup language, and the House in their markup for Oscar provided not less than $160 million for Argonne, and basically the facilities, the three facilities, Argonne, Oak Ridge, and NERSC, received close to what we requested. We had requested $93 million for ESNet, and the House said not less than $90 million. So we need to figure out what we do there. The other thing, the money for the scientific data center is actually in the NERSC line because we didn't separate it out last year. So there's about $2 million to help us start planning the data center. The House suggested that we spend not less than $250 million for research and not less than $15 million for computational sciences workforce program. Again, we have a recommendation to spend not less than $10 million and up to $40 million for the development of AI optimized emerging memory technology for AI specialized hardware, allowing new computing capabilities tailored to the demands of artificial intelligence. And when I put that into a spreadsheet and compare it to our request in the enacted, you'll see that the House has given us $15 million less than our request. The facilities, except for ESNet, are pretty much what our request is. ESNet has contingency, so 90 million is probably reasonable. CSGF, we are going to, it's a priority within the program, and we'll maintain it at 50, or at the request at 15 million. Exascale goes down because that was a planned exascale funding, so that's not, we had planned this all along. The exascale project is budgeted to this, so this is not a surprise to them. And we should be able to spend more than $250 million in the research program. Did I stop here for questions?
Yeah, it's Vint. I had a question about the previous slide was on special purpose hardware for AI efforts. At Google, of course, we've invested heavily in TensorFlow hardware. Are you making use of the commercial cloud hardware as well as designing and building your own?
Actually, I think, you know, a lot of the NVIDIA chip has some TensorFlow in it, and we do in that case, but we don't actually have contracts with the commercial cloud to use that hardware. I would think as we go forward, and as we're looking at what happens in the next generation of computers that we might put on the floor, I think there's a chance that we should have, you know, a talk to the cloud vendors, and maybe we can work together to get the computer vendors to develop code or to develop hardware.
I guess
go forward that we both could use.
The question, I guess, is whether it's possible to do any workloads that are unclassified and therefore could be run on a public cloud as opposed to having it in-house in your own data center.
Oh, no, we have a number of the programs already do that.
Okay, that's really the gist of what I was getting at. Okay.
And certainly that, as we think about the data facility, that's one of the alternatives we have to consider.
Mm-hmm.
All right, I see
Susan?
Hand up, and then Jack and Jill, you were unmuted for a while, but I don't know if you wanted to follow after Jack. So Susan?
Hi, thank you. Well, I am super excited to hear about your HPC data facility. I have two questions related to that. Will this data facility be somewhat structured a little bit like how you structure, for example, NERSC or the other HPC facilities where researchers can request time and capabilities to be able to use the facility, or is this more of a management facility? And the second question is, how does this relate to the pure data resources? Are those the beginning parts of the facility, so that will be where the main data impetus will be provided, or how do these two elements work together in your mind?
Yeah, okay. I would consider this facility much like our other user facilities, so they'll be open. And how we, you know, like I said, we're right at the beginning of planning, but I expect it to be a user facility and to be open to all, not to be just a management facility. And one of the things that I think is key is we have to make sure that and this is where ESNet is a key component for everything that we do, that access to that, the pure data resources are as streamlined as possible, so that as people using the data facilities, or say a light source, and they want to look at data, you know, from one of the pure data resources and bring it into a simulation to help, you know, guide the experiment, that's easy to do.
All right, Jack. Susan, did that answer your question?
It absolutely did, and I just want to, you know, +1 on that concept. I think this is really what's needed in the data compute world. So, fantastic. Thanks.
Thanks, Susan.
Jack?
Barb, I have more of an observation than a question. your previous slide, slide 17, shows about a 2.5% increase in the budget for Oscar in the request over what was enacted in 21. And I thought I heard Steve say that the Office of Science was going to get a 5.9 increase in its budget. Did I get that right?
In the overall Office of Science budget, that is never 5% for each program. So other programs probably got a higher increase to fix some problems that had, and we got a lower increase.
Okay, so we just didn't get. Yeah, so we just aren't getting the average. We're getting below the average.
Well, to be fair, Oscar had been getting increases when others in the previous administration, where some of the other programs were not getting increases. So it's just the way the budgeting works.
Thank you.
I guess maybe to follow up quickly on that, Barb, could you maybe frame a little bit of this in the context of the federal discussions about plussing up research budgets in general? And just, kind of where the Office of Science and Oscar, how that played out in relative to, the notion of the U.S. needs to increase its investments in basic research.
And I think, I think this is more of a Steve or Harriet question, but certainly Oscar has benefited because I think of the enabling technologies that we do in applied math and computer science and our focus on AI and now quantum. I think it depends on a lot on if you look at the Office of Science budget, we've had considerable growth over the past few years in quantum because that's a technology that's coming on board. And I think that's fundamental basic research. This is, it's key to many of the things that we do in the Office of Science. So we've seen growth in AI, machine learning, and quantum. We also have a number of large projects that we've started at the same time, which is key to the entire research infrastructure. I'm not sure if that answers your question, but I think right now the focus on the new administration, as Steve pointed out, is on the applied programs, and I think there's a lot that the Office of Science can do in conjunction with the applied programs.
All right, thanks, Barb. I see Roscoe has his hand up. John, you're unmuted. Are you wanting to ask a question as well? Okay, Roscoe.
Yeah. You started talking about it, and Dan mentioned it as well. But it would be useful for me to understand how the math and computing research budgets have trended as exascale trended down and as quantum and AI trended up. Those were, in the last time I was thinking about this, those were the kind of buckets we were looking at. And it would be useful to see. I mean, I think it is all going in the right direction, but quantitatively, I can't read it off from these tables.
Yeah. Well, I could go back and update the table that you had in your transition report. But my view is AI is applied math is so critical to AI that a lot of our growth and a lot of our focus areas, we've been focused on the priority research directions that were identified in our scientific machine learning basic research needs workshop. And so that's kind of guided our applied math programs and investments in the last few years. But we aren't where we were pre-exascale.
Yeah.
All right, I don't see any hands. Are there any other questions for Barb before we let her go on? Okay, thanks.
Okay, so now I'm just going to quickly go through what we actually have done in 2021 besides hire people. we have early career. We were fortunate to be able to select for Oscar's program 10 new early career fellows. Freddie Avzed from Indiana, Anu Das from Drexel, which is a new institution for us, Manuel Endres from Caltech, Russell Hewitt from Virginia Tech, Catherine Isaacs from University of Arizona, Aditya Thakkar from University of California, Davis, Shindai from Argonne, Drew Curry from Sandia, Robert Say from Berkeley, and Nathan Talent from Pacific Northwest. And you can see from the research areas on the right that they cover applied math, computer science, and quite a bit focused on AI, but we also have new fellows in visualization, multi-scale math, and certainly in quantum information science. As many people on the listening to the call today know that we had several funding opportunity announcements last year or this year for the first time in a long time. And thanks to bringing in Hal Finkel, we were able to have a computer science call focused on actually computer science on XStack programming models, runtime systems, and tools. I think the announcement for that has been out and is on our website. The other ones, I think we're waiting on final selections before the announcements are out. We're focused on expanding some of the work we started a couple of years ago on developing components for quantum networking. So we had call and entanglement management and control. ICDC is one of our first solicitations under the Integrated Computational and Data Infrastructure Initiative. Another one of those is the 5G enabling innovation, where it was a call just to the labs to have them start developing research tools and techniques using 5G. In partnership with basic energy sciences, fusion energy physics, and nuclear physics, we had a call on microelectronics co-design research and in partnership with the programs. We had several math calls.
Barbara,
Yes.
Before you go on, can you go back to that new investigator slide? I just had a quick question, mostly out of, I think, ignorance. So I noticed that the distribution of recipients from universities and recipients who are at the labs was about 50-50. Do you have some predetermined algorithm for what that distribution will be, and how many from a single lab, or they're completely blind to where the applicant is from?
I can say that universities, they are allowed, the floor and the ceiling for a university is 750 is the floor, $1,000 over 5 years. Where a lab is, those researchers, because of the cost of the lab, can request up to $500,000 per year for 5 years. So the distribution is primarily on what the budget can afford.
And those are direct costs.
Mm-hmm.
Those numbers.
Direct and indirect. Yeah, direct and
it's
indirect.
Total cost.
Yeah. Mm-hmm.
Okay, thanks.
Yeah. Okay, and so just briefly, the math requests. We're actually doing data intensive scientific machine learning analysis. We had an express. Express means they're 2-year awards, fully funded, and just for high impact, approach. And in this case, it was on randomized algorithms that followed on to a randomized algorithm workshop that we held earlier this year. Data reduction is primarily to focus on data reduction techniques and algorithms to focus on facilitate more efficient analysis and use of massive data sets that are produced by the observation and experiments. And that was a joint call actually between our applied math and computer science program. There was an increase in the budget in the request, but we also had funding this year to start support for regional test beds in support of the workshop we did on the DOE Quantum Internet Blueprint Workshop. And then our final solicitation is one that we hope to partner some of our applied mathematicians with a program that NIH is standing up, the Bridge to AI program, and focus on privacy preserving algorithms, because we feel that this is an important area for OSCAR to get into so that agencies like NIH are able to take advantage of our high performance computers at Oak Ridge and Argonne. I mentioned just briefly the National Virtual Biology Lab, and I know Michelle will talk about it more, but in December of 2020, Ben Brown co-chaired with Talia Meltzer a virtual roundtable of the scientific user facilities to actually discuss what happened during COVID and what the facilities' responses were, the best practices, and what innovations we could adopt going forward. And a lot of that information, especially in the computing and data resources section, will have highlighted the numerous challenges and opportunities that exist for the facilities and will inform what we're doing in the integrated computational and data infrastructure as we go forward. This, I think we just posted this on the web, so it should be available off our website. Something I don't talk about often is our interactions with other agencies. And this year, well, actually last year, we finalized our agreement with NSF and also NIH on the cooperation and funding for the NSF Collaborative Research in Computational Neurosciences. And I didn't mention that in our funding opportunity announcements because it comes out through NSF. But even more importantly, we recently established with NSF a joint oversight group for quantum information science between NSF and SC programs so that we can coordinate what we're doing and actually facilitate observation of each other's workshops, reviews, and making sure that the program managers are sharing information across with each other. And the other thing that we'll talk about later at ASCAC later this afternoon is a renewed memorandum of understanding between the National Cancer Institute, the Office of Science, and the National Nuclear Security Administration to fund the joint design of advanced computing solutions for cancer, which is JADAC. So I think Emily Greenspan will talk about that collaboration, and just to give you a highlight, then we'll have, I think there's a new charge that we'll talk about as well. And I want to come back to this. I saved this for last because, you know, we get reports from ASCAC all the time, and I don't want you to think that we ignore those reports. And there was a lot of effort that Roscoe and his team have put in on the software storage, on the transition from exascale task force. And so what I just wanted to give you an update on what we've done within OSCAR. We have actually established a task force, a software stewardship task force that's being led by Hal Finkel and Ben Brown. And and we want them to study the challenges posed by the increasing complexity of software ecosystem for scientific and high performance computing, and really focus on the upcoming transition from exascale computing, which has been supporting much of that development for years. And the charge, again, was substantially shaped by the recommendations by the ASCAC subcommittee. The software task force so far has recognized that nearly all computational science and including computer science and applied math research, depends on building on previous work. We don't start from scratch anymore. The software ecosystem will continue to evolve past ECP. And if we do our stewardship well, we hope to promote thriving careers, diverse inclusion careers in scientific software. And so in light of the ASCAC recommendations and other feedback, the task force recognized the multifaceted nature of sustaining the software ecosystem, including training on software usage, support for building and maintaining diverse software, infrastructure for software packaging, hosting, and testing, establishing governance processes. A lot of this we've learned from ECP, collecting information from user and facilities. Again, we learn this from facilities on what their needs are. Software engineering resources to assist with the maintenance activities of key project and providing support for continued development of key projects. The task force has already met with a Roscoe subcommittee. They've also met with ECP. They plan to meet with the division directors, from the labs which compose the Computational Research Leadership Council and other science funding. And they're preparing an RFI to seek broad feedback from the community. And they hope to attend, but again, it will be dependent on DOE travel policies, SC 21. So people interested in meeting with them should contact Hal. Vent, you have a question?
Yeah, I'm just thinking about the last two slides, particularly the one just before. You had a list of desiderata with regard to software ecosystem. And I've been talking a lot and listening a lot to several issues associated with the way in which we use software. I know we're heavy users of software libraries, and increasingly a lot of people are using open source libraries, but I've become very uncomfortable with the reliability and quality of the software that's available that way. And I even worry about internal maintenance of software libraries. It's not you don't get rewarded much for library maintenance, and yet it's so fundamental to the reliability of the stuff that relies on it. So I just wondered where that sits. We just had a lengthy discussion at the Software Engineering Institute on this topic that was led by, the advisory part was led by the gal who used to be at NSA and is now at Oak Ridge.
Frankie.
Yeah. Yes. Thank you. Duh. So there's a report that came out, and it might be of some interest to you about trying to make sure that we aren't building a very fragile house of cards. And of course, this gets even more hairy when you start thinking about supply chain issues and software and hardware that to find their way into it that turn out not to be your friend. So I just wondered whether that pops up in this list somewhere.
It will, I think, because I have had conversations, similar conversations, and I have to say that one of the concerns with us going forward with software we've developed in the Exascale Computing Project, where they brought together a number of libraries, they've developed policies so that you can make the codes interoperable, and actually they developed test suites. So we want to make sure that software remains as robust as it is going to be today on the Exascale machines going forward. So everything you brought up is key to what the sustainability task force needs to think about.
So I have a hardware question, but I don't quite know when to ask it. So I'll take advice about that.
Well, I think I have one slide left, and then I think if Dan thinks there's time, you can ask questions.
Okay.
Yeah, we'll make some time. I want to make sure there are time for questions. So Barb, why don't you go ahead and finish the official presentation And then we'll throw it open.
Yeah, the last slide I have is we have DOE, Office of Science has joined government delivery. So if you want updates in between ASCAC meetings about things going on in OSCAR, just go to the Energy Science / Office - Science and select what mailing list you want to be part of. So with that, I will stop sharing my screen.
All right. Matt, you had a hardware question you said, and then we'll see if there are other questions.
Okay, this one is highly speculative and kind of out of left field, but there's been a lot of discussion about the state of American chip production capability, particularly when we start looking at the Taiwan facilities that are running in the 2 nanometer range, and the scary potential that China will interfere somehow with that production capability. I've heard numbers as large as $50 billion floated around, especially in this period when trillion-dollar numbers are common, about the possibility of building a US-based fab that would be shared by most of the chip makers, as opposed to having everybody fighting with each other and winding up making competing investments, as opposed to being able to rely on a high-end production capability and then focus on chip design as the primary mechanism for business. Is that an idea that is worthy of some DOE or ASCAC discussion?
I think there's already been discussion within DOE for a number of years. There's an interagency working group on microelectronics, and we've been plugged into that. I can't remember if we actually had somebody talk about that before, but we certainly can bring somebody in to talk about it, because it is a concern for us, where we're going to get our next chips and making sure that we're competitive. Now, I have to say, I've said this before, my new best friend is Linda Horton, who is the AD for the basic energy sciences, because I'm counting on new materials coming out of that group that's going to help me with computing in the future. And I can tell you, I can look in my crystal ball today and I can't tell you what the computers are going to look like in the next 5 years.
Some people will remember Sematech way back in the 80s, when the Japanese were launching their 5th generation effort. And so, yeah, it just seems like, well, gosh, maybe there is a kind of parallel there. And maybe this is time to put something here in the US that's absolutely state of the art.
Yeah, and I'm not sure, but in the National Defense Authorization Act last year, they passed the CHIPS portion of that, which I think tries to address that.
Thank you.
Other questions for Barb about any of the things that she presented? Roscoe, your hand.
Yeah, let's see.
Roscoe.
Yeah, hi, just briefly, I did want to thank you and compliment Hal and Ben on their work in taking a systematic approach to looking at elements of that transition report. And so thank you for that, and thanks to folks who are working on that. I also wanted to just comment in response to what Bent was saying about the software and engineering, that we also thought it was important to consider career pathways and support for engineering activities, as you're aware, and I hope that's being thought through as well for sustainability of software.
Other questions or comments?
This is Jackie. I have a quick question for Barb. In your discussion about maintenance and extension of ECP projects, especially the software that's being developed, is there some consideration for including or adding data science, AI, ML methods and libraries at scale? Because these ECP codes will operate at scale, and a lot of the workflows that we're considering will include data science elements that need to be part of that part of those simulations.
And yeah, I agree with you. And I think if I can figure out how to do it, the one part of ECP I'd like to keep is the XLearn that brings in the co-design center that brings in 8 labs to focus on this and see if we can expand it. So that's, I think you're right on. And I assume Margaret Lentz is hearing what you said.
Okay, and especially getting the data interfaces right so that a lot of the applications can tap into that.
Yeah, that's also key to this integrated computational data infrastructure that we're doing as well. And another thing that we learned out of the COVID-19 HPC consortium is we got to figure out how to make data more interoperable.
Great.
I'm just looking to see other questions. I do think Vince's observation is an important one. Increasingly, the poker chip minimum unit to sit down at the table and play starts with B, not with M. And how we think about what appropriate scale or responses are, I think is increasingly important. And so just as that philosophical observation, and maybe to connect to what Jackie said, you know, I'm just going to segue on, Barb. So thanks very much for that overview and state of things from Germantown is, you know, the complexity of heterogeneous architectures and end-to-end code design raises a whole bunch of new issues about operating systems as well. And so our next discussion, Al Finkel is going to lead about a roundtable discussion on OS system research in this brave new world. So Hal and participants, go for it.
All right, Dan, thank you. Can you hear me?
Yes.
Okay, great. Let me share my screen. Okay, can you see my screen?
Yes. Good.
Okay, great. So thank you very much. And I will try and go relatively quickly to get us back on schedule. Thank you for your attention. This presentation is to inform you of the outcome of a very interesting roundtable discussion that Oscar hosted on January 25th of this year on operating systems research. The discussion involved several participants. I'll get to that in a moment, but I would also like to point out that we had over 100 registered public observers who joined to watch and listen to the conversation. And I thought that was great. We had a selection of invited speakers from outside the DOE laboratory complex. They came from other parts of the world. We had speakers from universities, and we had 2 international speakers. Blas from Riken was kind enough to join us at like just past 3 a.m. or something his time. So we're thankful for that. And we had a very interesting conversation. We had participants from many of the DOE national laboratories. And the agenda for the discussion included discussion topics on extreme heterogeneity, on edge computing, on data and artificial intelligence, on containers and virtualization and programming environment management, and on resiliency and correctness. And the outcome of this roundtable discussion was that the participants self-organized and collectively authored 2 white papers. And so what I'm going to do now is present to you the main findings and conclusions from those white papers. The 2 white papers are themselves posted along with this presentation on the meeting presentations page. So those are now publicly available on that webpage. All right, so the 2 white papers, one is on research opportunities and operating systems for high performance scientific computing. And the second white paper is on research opportunities and operating systems for scientific edge computing. And those 2 areas have unique challenges. And so the participants decided to author 2 separate white papers. Okay, so first I'll talk about the high performance scientific computing white paper. The next set of slides are all really extracts from those white papers. So these represent the views of the authors of the white papers. And you can see a number of the participants got together to author this white paper. They called out three main areas of focus that they thought were important. One is full stack co-design for extreme heterogeneity and scalability. One is adaptive management and partitioning of resources. And the third is smart supercomputer systems and facilities. So I'll go through each of these in turn. For full stack co-design for extreme heterogeneity and scalability, they noted a number of interesting current trends. One trend is, of course, that heterogeneity is increasing, the scale of systems is increasing, and as a result, the amount of data migration between components, between parts of systems, and between systems is greatly increasing. They noted that current software must increasingly be optimized and specialized for different kinds of hardware, and that the number of different pieces of hardware in current systems that have their own programming environments and programming considerations is increasing. So, you know, this is CPUs and GPUs, but also smart NICs, processing and memory kinds of components and other things, TPUs and AI accelerators. All of these things have their own programming environments, their own special considerations, which makes things challenging. And they further noted that systems research and development increasingly requires co-design of both hardware and software. And that with high quality open source hardware designs and fast cycle accurate simulation tools, it is now possible to rapidly co-design pre-silicon hardware together with full software stacks. And this has been exploited, and the authors called out an example, which is how for RISC-V, the kernel-based virtual machine capability was prototyped with a full stack on FPGAs, in order to validate the design and provide feedback on the design before that capability was baked into the standard that was then used to generate production hardware. All right. For research challenges and open questions, they pointed out that proving out new operating systems ideas is difficult to researchers if they have limited ability to affect hardware designs and they have limited access to large-scale HPC platforms on which custom operating system software can be booted. And so, a partial mitigation of these challenges is performed by prototyping on FPGAs and using other kinds of simulation tools. And that operating systems research in the context of full stack co-design can address rapidly developing novel accelerator hardware and accompanying system software. It can address common interfaces for heterogeneous hardware, enabling effective operating system management, autonomous resource management that reduces the burdens on users, and system-wide security that enables breaking free from the root is special model that is common in HPC systems. Vin, you have a question?
Yes, thanks. Sorry, it takes me a while to go find the microphone. I'm just wondering, I know nothing about hardware, so this is a naive question, but when you simulate something on an FPGA in anticipation of doing an ASCAC, is there a distortion in the way things perform that would be misleading?
That's a very interesting question. So people use FPGAs in two different kinds of ways. One way is as accelerators themselves, and another way is to simulate at a cycle level what hardware will do. Now, with many caveats, I will say that the way that you optimize a program for FPGAs is different from the way that you optimize code that will be used to generate an ASIC. But if you use the ASIC targeted code on FPGA. It will run slowly and also doesn't necessarily have things like a full cache hierarchy. But with those caveats, you should be able to understand the main performance characteristics of an architecture. And in fact, for large simulations, sometimes people group together multiple FPGAs in order to perform these kinds of experiments.
So I just wonder about clocking, race conditions, high density chips, and the need to have multiple clocks running, concurrently. Very little of which shows up in my imagination anyway in an FPGA implementation. I may be just running on empty here, so don't let me chew up too much of your time with it.
Okay, yeah, I mean, the timing difference, can be an issue, but it's certainly a well-known one for the engineers and scientists who work on FPGAs, and they take specific steps in order to understand where those differences are going to cause, sort of relevant effects.
If I may, Hal, just
yes.
to answer it from what companies do, they do use these large-scale FPGAs to validate functionality of design. Race conditions and things like that, we lean heavily on formal to extinguish those, especially in a security context. So something like KVM is kind of scary in that it's a virtual machine, it's security, it's all about race conditions and side channels. Yeah. All of those are going to be different on an FPGA, so you really have to rely on formal for that. But happy to have a discussion offline on it.
Yeah, I'd like to learn more about that. Thank you so much.
Yes, thank you, Eric. And also, Eric, thank you for joining this roundtable discussion. He was an invited speaker at our roundtable. Okay, so the papers list a large number of open research questions and opportunities, about how we think about operating systems managing extremely heterogeneous systems. What are the right kinds of interfaces to make that possible? To what extent can you make those runtime systems autonomous? Can you use co-design in order to understand how you can design the systems to reduce the burden on the user in terms of how they manage those resources, how they assign work to those various pieces of hardware and do so in a way that's efficient. And can this be done portably in a way that will allow applications to move between systems with a minimal amount of effort. So there's, of course, the design components here as well, designing systems that do on-the-fly data optimization, compression, transformation, placement. So, this is a question about the operating systems themselves, right? But also, operating systems are really tied to the hardware capabilities underneath them. And so, there are questions about what capabilities the hardware provides, what capabilities the operating systems provide. In this context, of course, there are, particular concerns around security, how we enable system-wide security, how we, add features to these systems that, enable us to have the kinds of trust models that we need to enable open scientific collaboration and, the involvement of multiple parties, of, federated computations and so on, while also making sure that we can maintain the requirements that we need. And also to facilitate the movement of workloads between the cloud, including the commercial cloud and our HPC systems. All right, so if there's success in this area, the authors point out that it will become feasible to develop and economically deploy domain optimized silicon targeted at DOE computing workloads and deliver world-class efficiency and performance. And that we'll be able to produce highly credible operating system functionality, hardware designs, and actionable information that can be used to influence our vendor partners and the wider computing ecosystems, which will ultimately lead to more efficient DOE supercomputing platforms. For the white papers, I asked all of the authors to specifically think about which research communities would be contributing to these kinds of efforts. so we know, who we need to reach out to. And of course, the operating system research community is an obvious participant here, but also there's a vibrant open source hardware community in academia and in industry, I should add, and also leveraging a new class of hardware vendors that are emerging to help customers develop domain optimized targeted hardware for workloads is important participant here. All right. So the next area was adaptive management and partitioning of resources. And again, there are a number of applications now that are composed of multiple components, right? They're complicated workflows. Sometimes they have to be rewired, so to speak, dynamically. The idea that you're going to make a static set of decisions up front in terms of workload placement and execution does not lead to an optimal execution. And so leveraging those capabilities becomes harder. In addition, running a diverse mix of workloads on a node can improve overall resource utilization. Traditionally in HPC systems, this is avoided because, especially in multi-user scenarios, because it tends to introduce performance variability. But of course, given the trends of our current systems, as each node gets more and more powerful, this is something the authors felt that we might reconsider and research. Now, in terms of scientific workflows, there is a current lack of standards that hampers the construction of composable and extensible workflows. And so right now, nearly all multi-component applications in workflow assume a different model for partitioning and selection of resources and so on, and they're not composable. This makes the applications and the workflows brittle, and it's a barrier to extensibility. So another thing that the authors called out is that virtualization techniques are popular. They are a popular existing solution in cloud environments. And they do offer a partial solution to some of the challenges that we've pointed out. They've traditionally been avoided in HPC due to overheads and some other kinds of concerns. And that HPC-specific multi-kernels can also offer lower overheads at the cost of additional implementation complexity. And so that's an important trade-off that would need to be weighed. Okay. And finally, the adoption of containers is increasing. This is true on our HPC systems as well as elsewhere. But these bring new challenges around composability and around efficient workflow integration. And that's really important. So extreme applications are already facing limited memory capacity and bandwidth. There's not really any widely accepted standardized interface for exploiting deep memory hierarchies. And there's also a conflict between how much of the memory hierarchy to expose to users, which can be complicated, and how much to hide behind virtual paging-based interfaces and so on. All right, and so the challenges here have to do with how the programming languages, compilers, and environments are going to be extended in order to expose information about the systems and allow users to use that information, and at the same time allow the system itself to be dynamic and to adjust to the workloads as they are, and building performance models in order to support decisions to integrate this user-guided and automated information. How you construct these sort of data-centric abstractions, and how you really take advantage of all the different capabilities on the node, including things like smart NICs and other kinds of accelerators. How you support containers in an HPC environment, noting the challenges around composability and so on that we pointed out earlier, and to manage these trade-offs between static allocation and partitioning and versus the dynamic nature of the workloads. Okay, and then also, okay, said that already. Okay, so the benefits of success would be middleware capabilities that address these challenges. I'm going to go a little quickly because I know I'm low on time here, and improve resource utilization, improve productivity, and opening the HPC systems to a broader, more diverse set of workloads. Both because of interoperability with cloud resources and also just because the more dynamic nature of more complicated workflows are supported. And the research communities that contribute to this are many, both from facilities, from middleware and programming abstractions, from the cloud and edge communities, and so on. Okay, now for smart supercomputer systems and facilities, I'll go over this briefly. There are important trends in operational intelligence enabling, but I should say that currently the kind of toolbox that's available to system administrators and system designers is limited in terms of corrective actions that can be employed and how systems are managed. And there's wide interest in having more automated decision-making and collecting the data that's necessary to drive those decisions. And so, this is going to provide motivation for designing, for researching more automated decision-making and data and algorithms that drive that, and understanding the trade-offs in employing those algorithms, plus understanding where the community can leverage software that's used in other industries in order to manage these kinds of systems. All right, this second white paper is on research opportunities for scientific edge computing. And the idea here is that scientific experiments are generating an increasing amount of data. They're growing in computational complexity and operational complexity as well. And so there are a number of unique challenges for operating systems in this space. Now, of course, edge computing is becoming an important part of HPC environments. The data from edge computing is streaming, directly from large-scale instruments and experimental facilities into HPC environments. We have large-scale data collection analysis from distributed sensor platforms, and we have a desire to do real-time or near real-time steering of experiments based on high-performance computing calculations. So, and the current state of the practice here is very hands-on. There are experiment-specific solutions that are being developed, but they're not really reusable in general across different experiments. And the result here is that we know we can do better in many areas. And so the authors of this white paper called out particular examples, such as in material synthesis, where we currently accept reduced precision in experiments and performing more experiments than we might otherwise need to, because we don't have that kind of real-time feedback in order to detect defects and adjust running parameters. And so, the current software, as I said, it's not really interoperable. It's not really reusable. Data formats and communication protocols and so on are often custom. And so the research challenges and requirements here are really to address this current state of the art and to improve it in important ways. From the operating system standpoint, extending the domain of trust and enabling security policies that can extend to large distributed systems on the edge is a particular challenge. We're trying to maintain systems that can be used for open scientific research, and so we need to have adaptive security policies, protocols, and implementation strategies that can support that, but maintain trust and scientific integrity in the result. And so the challenge here in operating systems research is to have operating system structures, algorithms, and implementations that can support this kind of those kinds of scientific requirements. There are a tremendous number of interesting requirements that come from the desire to have sort of self-driving laboratories, to have artificial intelligence-driven design, and again, a lot of the interfaces there are currently custom interfaces. They're not sort of well integrated into a composable system, and so the authors are calling out that this is an area that is really in need of investment. And so, moreover, what happens as a result is that there's a limit on the speed on which experiments can get feedback from computation and from theory. And so all this is sort of designed, and there are many, many pieces to this, not just operating systems, but the community felt like there are operating system pieces in here that are key drivers and sort of sit on the critical path of really enabling this real-time feedback and control. And this is important in many kinds of experiments where for instance, biological samples have limited lifetimes, and real-time feedback is needed to discover and treat manufacturing defects in advanced manufacturing experiments, and so on. And making sure all those pieces can fit together into an integrated system, that there's appropriate levels of abstraction and so on, are key features of that operating systems need to provide. And so, and for large-scale distributed systems, sort of top-down centralized resource federation and control is not likely to scale, be resilient, or sufficiently dynamic. And so having systems that are really designed to be distributed and scale to the large scales that are needed for these challenges is important. And so as a result, the abstractions that the operating systems provide need to, in many cases, provide explicit performance and quality of service measures. They have to include information on resource availability, which can be dynamic, and for control and configuration of distributed resource selection. All right, so all of these things lead to open areas, many of which I've just mentioned. In addition to that, of course, leveraging artificial intelligence and machine learning for surrogate modeling in order to steer these resource decisions is important. And it's really also important to understand sort of what role humans play on what timescales and how to account for that. And also to integrate the ability of modeling of virtual instruments as digital twins in order to guide resource selection, to guide experimental maintenance and other factors is important. Okay, so the benefits of success, of course, are to address all of these challenges, to allow HPC systems to expand, to support emerging classes of workloads based on large-scale and distributed online data collection, integration of experiments, and so on. And to do all that, while maintaining trust, to have appropriate security guarantees and policies to, and then to sort of plug into these larger challenges of enabling self-driving laboratories and smart manufacturing and AI-driven design and so on. And so the authors of the white paper called out a large number of research communities who they thought would be involved in this process, not just the sort of existing research community around operating systems in a traditional sense, but also research communities around distributed systems, around edge computing, the HPC operations personnel at the facilities, the artificial intelligence and machine learning communities, the decision sciences communities, and the instrument science communities. Okay, so I know I went a little bit over. I apologize, but thank you very much for your attention. And if you have any questions.
Yeah, thanks, Al. You started a little bit late, so no, I don't worry about that. My geek spidey sense is tingling. I'll try to keep that in check and see if there are questions from other people. Bruce.
Yeah, Hal, lots of interesting work here. So historically, we've thought about operating systems for HPC platforms as the core research area. I want to argue that should be changing. It was implicit in your talk, but it wasn't called out explicitly. So we've traditionally viewed runtimes as a scourge of performance, and so we've typically had very simplistic runtimes for HPC platforms. As we're getting to the more complicated systems with heterogeneous hardware and much more complicated workflows, I think we need a lot more out of runtimes than historically we've focused on. So I would encourage you to rethink. Even the title of this workshop was focused on operating systems. I really think the aperture needs to open further. And the real interesting topic right now is runtime systems, not operating systems. So just something, a different framing that I think is worth thinking about.
Yeah, thanks, Bruce.
Yeah, that's a slightly religious question about microkernels and runtime systems and where the boundary is, but point well taken, Bruce. Susan.
Hi, thank you, Hal. The white paper and your presentation are really thought-provoking. I do appreciate them. I have a question. I hope I can formulate this. It's not my area of expertise, but I just want to get your thoughts on the push and pull between what I feel is really important, which is adaptive management in compute, and the pushback perhaps from vendors who will not be so keen on adaptive OS, and then the researchers who may also have some concerns, at least in my community, about the number of iterations on the software to configure to different types of adaptive OS systems. So love to hear your thoughts on that.
Okay, well, I think that the goal of adaptivity is really to help users to manage the resources that are available and to help them use the machines effectively. And so, there's an extent to which I feel like if people are developing adaptive software that is getting in the way of what users are trying to do instead of helping them, then something is wrong. And I think that if the portability challenge is thought of solely as a static problem, then it's not likely to succeed in the context of systems that are becoming increasingly heterogeneous and dynamic. So if you and so I mean, I'll say, I mean, I feel the pain of users who are facing the challenge of porting their software to different platforms and dealing with the sometimes idiosyncratic nature of the way that they perform and provide different kinds of capabilities. But at the same time, I think the focus of our research effort going forward has to be on systems that address those challenges and really provide users with an enhanced ability to take advantage of future computing capabilities and resources. And I think to the extent that dynamic and adaptive runtimes are part of that picture, I think that we need to focus on kinds of solutions in that space that will help, that won't get in the way. They are systems that where users can direct the operation of the system when needed, but are in general helpful to taking advantage of resources.
All right, so I think Richard and then Martin have questions.
Hi, Hal. My question is whether you see a role for formal methods across both programs in this operating system research. In the general operating systems research community, it's considered to be almost required to have a proof that's formally specified and delivered as an artifact with new operating system technologies, certified operating systems, and so forth. And in the HPC case, where you want to make assertions about the behavior of objects at scale, and whether you used FPGAs to simulate or not, you simply couldn't simulate at the scale required. I would think that such methods would be particularly necessary.
Okay, so I'll answer your question by first saying yes. In fact, I'm actually quite happy that as part of the ASCAC awards that were recently announced, we have some very innovative projects that are proposing to combine formal methods and other methods to do testing and verification of scientific software. The challenge, of course, with formal methods are numerous, one of which is they can be hard for non-experts to use, another of which is that they often have scalability challenges. And the research that has been proposed by some of the selected projects really have key insights that should allow those challenges to be addressed. in very important areas to our portfolio. So I think in this context, the answer is also yes. And as you point out in other spaces, formal methods are quite important. They are especially important for verifying security relevant properties. And many of the challenges that the authors of these white papers pointed out had to do with security, privacy, trust, integrity, provenance, and so on. And that's another area where these kinds of methods are important. So, I think that there are many ways of doing testing, verification, design, and development, but to the extent that formal verification can be used effectively, I think it's important and should be used.
Thanks, Phil.
All right, maybe in the interest of time, Martin, you get the last question.
Okay, thanks for indicating all the challenges that arise in the situation and the need for dealing with heterogeneity. I mean, I guess I'm kind of lined up with Bruce on this in terms of wanting to suggest that one has to think a bit more broadly, but I would also like to suggest that sometimes we're very good at identifying the problems, but less clear about thinking about some sort of relatively simple solutions. Right now we've got a whole bunch of really big machines coming in that are heterogeneous, but have sort of, uniquely distinct kind of architectures and distinct sort of user, vendor supplied solutions for dealing with heterogeneity. I mean, what we really need is something that makes it possible for applications in the same way that MPI came along to address that kind of challenge in a very simple but portable way. And it doesn't have to be as fancy or as clever as, many of the things that you've indicated that would sit inside the perfect solution. But there's a desperate need to do something that is portable and makes it possible for applications to run across all of these machines. We have Cocos and Raja, but they're kind of over towards the detailed code side in a way that's perhaps too fine scale. And we need something that sits above those, perhaps, that enables us to address this problem for many, many user codes without the complexities of some of those really good systems that do exist.
Yeah, so Martin, I think that's a very good point. And I think that we are trying to address the software challenges in our ecosystem. As you point out, I mean, the ASCAC computing project has had major investments in this area, including in frameworks such as Cocos and Raja and other C++ based frameworks in modernized Fortran and so on. There are also a number of investments in higher level programming models. With the advent of artificial intelligence and machine learning toolkits, people have been experimenting with the development of all sorts of applications, on top of things like TensorFlow and PyTorch and so on. And there are, and moreover, have been extending those kinds of toolkits to perform Monte Carlo simulations and particle-based simulations and all sorts of things. And I think that as we go forward, we will see that it's possible to create applications that can use higher level interfaces and can provide optimized solutions that run across heterogeneous platforms. At the same time, the development of those solutions and the development of specific applications will sometimes require kind of going down a level to optimize and take advantage of certain capabilities. And I think that what we're seeing is an ecosystem that has this broad spectrum. So, and I think that you'll have increased capabilities at the higher level and also increasing capabilities for portable programming at intermediate levels. And all of those things are important.
I will comment that while I see the complexity, I think we should look for simplicity.
I agree.
Well, as Da Vinci said, simplicity is the ultimate sophistication. So, Hal, thanks for this sort of really thoughtful overview of the workshop. Thanks for these great questions. Let's transition to our next discussion, and that's really Marianne is going to lead us in a discussion about challenges and lessons learned in expanding participation in computational science and engineering. And I'll just editorialize for a moment and say, you know, as we think about the literally missing millions of people that we need in the STEM workforce to be globally competitive, we need to capitalize on every mind that this country produces. And so look forward to talking about how we broaden access and include more people. So Marianne, floor is yours.
Okay, great. Thanks, Dan. And thank you for that editorial. It warms my heart to hear it. So I'll just bring up my slides here. Let's see. Okay. All right. So I assume you can all see my slides. If not, please let me know. I'm delighted to be here to talk about expanding the workforce, which is, as I mentioned, a subject that's near and dear to my heart. And I do know it's also important for the DOE, as well as ASCAC and ASCAC, which of course is evidenced by the charge to the Workforce Subcommittee back in 2014 that came up with a few observations or challenges that they described. The first one, just that the DOE labs are facing workforce challenges and need to develop more effective techniques to attract and sustain a full spectrum of talent. And in particular, the letter calls for new approaches for recruiting and retaining staff, especially those from underrepresented backgrounds, such as women and minorities. And now, 6 years later, last year, we saw the Oscar at 40 highlights, which again called out workforce challenges, and in this case described how it's just getting more competitive. You know, there are more opportunities for people with the kinds of skills that we need in computational science and engineering, so it's more difficult. So the problem in some senses is getting even harder. But the good news is there are things that we've learned to help with this. So I thought just to frame this conversation, I would start by just asking the question, why should we expand? Maybe this is obvious to everyone, but certainly we know that CSE is inherently complex. It requires really creative solutions and a lot of collaboration. And in particular, the mission-driven science that happens in the DOE labs is inter and multidisciplinary, which really translates to being a team sport. And there is plenty of research that indicates that more diversity in a team leads to more innovation. Again, to kind of set the framework when we start thinking about cultivating these teams of diversity, I wanted to just share a quote with you from this Leadership in Science and Technology Handbook. I'll just read it to you because I think it's really poignant. It is said that the truth shall set us free, yet we need freedom to discover the truth. Thus, leaders in science and technology must accept responsibility for the results of their work and for the means they use to accomplish it. Fundamental to that responsibility is respect for facts, for creativity, and for colleagues. And if we focus in on that last part of the fundamental responsibility for respect, facts, creativity, and colleagues in the context of expanding participation in CSE, you know, what we find is that, unfortunately, cultivating respect for colleagues from underrepresented groups has been quite elusive over the years. And that's known because of a lot of sources of attrition, which are well known and well studied, such as bias, discrimination, feelings of isolation if you're kind of the only one there, a lack of role models, confidence, social capital, as well as the imposter syndrome, which most of us actually suffer from at some point in our life, but people from underrepresented backgrounds tend to have a higher incidence of. And unfortunately, in some cases, we hear about harassment as well. These are all things that are working against us cultivating that kind of respect that we need to do the science.
So what I'm going to do today is share with you a little bit about some lessons learned and some challenges that were identified at the SIAM Computational Science and Engineering Conference this year. I had the lucky honor of co-organizing and moderating a diversity and inclusion panel. So we'll just share kind of what we learned from that. And then related to that, there's a couple programs that I'll talk about that we've been involved in, the Sustainable Research Pathways program, which really is targeted at recruiting what I call the unusual suspects, so the people who don't typically end up in the DOE labs. And then the broader engagement program, which we organize at the SIAM CSE conference, which is focused on cultivating the talent of these underrepresented people, as well as building community and trying to foster a more inclusive environment. So the SIAM panel had 3 parts to it. The first part was where we had stories. We heard stories from panelists who were people who are from underrepresented backgrounds, and they're living and breathing in the CSE environment. The second panel, we had a distinguished group of people leading organizations and leading efforts in DEI, diversity, equity, and inclusion. And then in the third part, we had a kind of a response session where people could respond to what they had heard, and a very interactive discussion and follow-up. So we were lucky to have opening remarks in this panel from Ron Buckmeyer, who is the new SIAM VP for Equity, Diversity, and Inclusion. This is a brand new position that SIAM has created, and he's the inaugural VP. We got to hear a lot of great things, and in particular, what I wanted to share with you was kind of his tenets for what he wants to do, or his charge he's given himself to guide the work that he does in this new role. And the first is that diversity is a fact. Well, we know there's diversity out there, and of course there's diversity in all different dimensions, not just the standard demographics that we tend to look at. But while there is diversity there, we know that it exists. Inclusion is optional. So it's not automatic that everyone is included. We have to make a concerted effort to make inclusion a fact as well. And then through diversity and inclusion, we can achieve the goal being equity. So for the first part of the panel, we had 3 panelists, and I'll tell you briefly a little bit about them. And then in the following slides, we'll talk about what we've learned from the panels. The first panelist on the left was Sally Ellingson. She's an assistant professor at the University of Kentucky. She is a single mom, and during school, when she was an undergrad, she's also a first-generation scholar. She applied for an office job so that she could get tuition reimbursement, because she was a single mom trying to support herself and her family and her child. And then she ended up going away from home and away from her support system to grad school because she heard that you could get money to go to grad school, and she applied for and received a fellowship. And then we have Derek Jones, who's currently a data scientist at Lawrence Livermore National Lab. He is from rural Kentucky. He talked about how he was the only Black kid in school, and he didn't really have very much access to STEM resources. And then we had Bonita Saunders, who's a research mathematician at NIST. And we heard some pretty amazing stories from her. She was kind enough to share a little bit about kind of her chronology, which led us to learn that she actually went to segregated schools in the South and lived through desegregation. And so she shared with us a little bit about what that was like, and how it was that she became the first Black to attend the College of William and Mary. Our second panelists included these 4 distinguished leaders in various institutions. Scott Collis, the director of the Center for Computing Research at Sandia National Labs, who's leading a number of efforts within his center as well as across the lab in terms of DEI. And then we had Lisa Crompton-Young, who's the provost and senior vice president of academic affairs at Morgan State University, which is a historically Black college and university. Bruce Hendrickson, who is on this call, who's Associate Lab Director at Livermore National Lab and is leading a number of DEI efforts across that lab. And then we had Maria Clave, who's the president of Harvey Mudd. So to move on to a little bit of what we learned, one of the things that really struck me was the discussion about being the only one and how the challenges that presents. So I'm sharing a few quotes from what some of the panelists said. The first one, I just wondered why any of these famous computer scientists don't look like me. So there's kind of this lack of belonging because of that. And in the second quote, he's talking about how he saw that, there's a Black woman who actually was one of the first people to help run some of the simulations that made space travel possible. And he notes, I didn't learn about that in school. So there are some role models out there, but didn't get the chance to learn about that in school. And then here we hear Bonita talking about it. It wasn't until I got to Old Dominion that someone looked at me. A professor looked at me and said, oh, wow, she's good. We got to put her in the PhD program. So they actually put me in the PhD program without asking me. So I'm thinking why it took so long. So here's a woman who's clearly great, smart in math. She applied for a master's program. They realized that she was really smart and they put her directly into the PhD program. But she's thinking, well, she talked about how she went to, an all Black school before and she got all kinds of recognition because she was so smart. But then when she went to a segregated school, she didn't get any recognition. No one really realized that she was smart. We also learned that sometimes the challenges are invisible. And that is, this quote here kind of speaks to that. I actually did not tell anyone in the program that I had a kid and that I was a single parent. I had nightmares that people would find out and that I would lose my fellowship. So that's kind of very interesting. So some other data that we received from Harvey Mudd in the panel. Maria talked about kind of what it was like there 15 years ago versus what it is now. Where 15 years ago was 75 to 80% Caucasian. Now it's only 30%. So they have managed to migrate that population in the students to a lot of minorities in the population now, and they're spread across the majors. And whereas 15 years ago, there was only 30% female population, it's now 50%. And that includes in the computer science, engineering, and physics departments, which are kind of notoriously underrepresented in terms of women. So some of the challenges that we heard about was regarding the role models. Why don't they look like me? They do exist, but I don't hear about them. The hidden needs of being different, causing some fear or shame. The basic needs that are taken for granted by others, like needing money to pay the rent and to support the family. And then we also heard stories about the explicit versus and implicit bias. And in particular, I note that Bonita talked about how she was trying to enroll in some math classes at the integrated school, and she was told that people like her didn't take math, so she really shouldn't even try that. And I want to just note that there is research showing that people from underrepresented backgrounds typically come from non-traditional paths and are more likely to experience these types of things. Some other challenges we heard about from the organizational level. So institutional organizational change is very, very slow. And there's many, many challenges. However, we did hear, even though it could take decades, that dramatic shifts are possible, that they can be realized, as we saw at Harvey Mudd. And then the other really big challenge that we had a lot of conversation about was the long-standing practices and policies and attitudes that are in place that really present challenges. And in particular, there was this kind of tension of this idea when, for people who are trying to advance DEI, that there's a trade-off. It's a zero-sum game problem, that there's a trade-off between diversity and excellence, when we know that's really not true, that there is excellent talent out there that comes in different forms. So in terms of moving on to some effective approaches, we heard about the changing the paradigm in the academic arena, adopting classroom and teaching models that appeal to broader demographics. Of course, this can be applied to DOE labs and work environments. We learned about how it takes both diversity and inclusion to get us towards equity. And then really important work is going on in some of the labs about taking strategic rather than tactical approaches to hiring. You know, we know that these proposals come in and all of a sudden you have to have people with specific talents. So what happens? You run to the well that you're familiar with and you grab talent, but that doesn't do anything to help you diversify the workforce. A lot of the people talked about using implicit bias training, and that was helping developing really meaningful partnerships with diversity organizations is another thing that was really helpful and successful. And then here's one that I think is really interesting to consider as well, and that is kind of retooling to cultivate the authentic self. So that respect for everyone that we need to pursue truth. So that's really retooling the environment to cultivate environments where everyone can bring their whole self to work. And most importantly, what we heard about was how important it is to work together to support and create inclusive environments. Other things that made a difference was clearly we heard about being recognized for their talent rather than being told not to even try. And really the message here is that there are talented people. They don't want a free pass. They don't want a free lunch. They just want to get the well-deserved recognition that they need rather than some sort of bias. Having an advocate really works. And we also heard that it doesn't have to, the advocate doesn't have to look like the person who you're trying to advocate for, but it is essential to have advocates and mentors who can help you. Remember, a lot of people from underrepresented groups, they're first generation scholars, so they don't have someone who's already giving them a roadmap for how to do this. And then last but not least, we heard a lot about how important it is for resources, programs, and opportunities for people to make it through the pipeline, shall we say. And with that, I'm going to move to talk about some of the programs that we've been working on to help in this area. And the first one is called Sustainable Research Pathways. We partner with Berkeley Lab on this. And the idea that this kind of came out of was to try to expand the network and diversify the workforce within the computing sciences direct area. So the basic idea is to build relationships centered on research collaborations. We worked on recruiting faculty who are working with underrepresented students. So initially we were just recruiting faculty who would bring students with them to the lab. And more recently, we've added a new student track so students can get involved in this on their own without their faculty member. Through this program, we also provide opportunities to the staff scientists to participate in the research collaborations, as well as learn and contribute to the DEI efforts. And this work is being done to supplement the existing DEI programs, as well as to make use of them. So in a nutshell, the way this works is we go out and recruit all these unusual suspects. We look at the applications, we see who makes sense to participate in a matching workshop where people get to learn about the research going on in the labs, and we learn about the research interests of the participants, and then we do this fun matching process. And if you match, then you move on and try to apply for funding for the summer research experience. So a little bit of a data for everyone about this program. So we ran our first workshop back in 15 was our first cohort that came out for the summer. And since that time, we've had just 450 people applying to attend, representing about 1,100 students. About 150 have attended the workshop. 90% of the people match, so almost everyone matches. And by the way, a match is I want to work with you and you want to work with me. So it's a two-way match. And then about 80 faculty and 200 students have conducted research over the summer at the lab. And this is taking on a larger and larger share of the summer internship program at Berkeley. So here's a little data about the students who have participated in the program. We have an intentionally really targeted undergraduates where we believe that you can have a more impact on their trajectory. Well over half have been for undergraduates, well over a third female, almost 20% African American, a quarter Hispanic, and a few with disabilities, and a large number of first-generation scholars as well. So we did a little bit of a survey a few years back to find out, how the program was going and hear from people. And I'm sharing here just a few results from that analysis we did. And on the left, you can see about half of the people, half of the students say that this program changed their vision of themselves as a scientist. So it really, really boosted their confidence. And we do believe they're also changing their trajectory. And then initially, before the internship summer experience, about 3/4 of the people were planning on, of the students were planning to go get a job in industry before, and then afterwards, only 1/4 of them remained with those plans. And instead, you can see 1/4 of those people decided to go on to graduate school. Some of them became unsure, which we think is fine because they're just kind of rethinking their plans. And then, of course, some go off, decide to do something else, such as take some time off and then apply for graduate school. So in summary, this program on a programmatic level, we basically have brought together people that would have never otherwise met. So we're bringing people in from institutions that the scientists have never even heard of and would never consider trying to explore collaborations with. And on the other end, the people who we're bringing in, they don't know anything about the DOE labs. And so we're really bringing together people who otherwise would have never met. We've started very productive new research collaborations, and we've showcased the lab work externally, which I'll talk about next. In terms of the faculty, they've been able to take on a lot of really vibrant research projects. Many of them are in teaching institutions, so they don't get a lot of time to do research. We've raised their awareness of DOE labs, and they've told us that now they feel confident to tell their students, hey, go do this internship because I've been to the labs. I know how great it is and what kind of environment that is. They've also told us that they've taken what they've learned back to their institutions, and it's impacted their teaching and technical skills. For the students, there's many impacts. I highlighted just a couple. Certainly, we've changed their trajectories, and many of the students talk about this as literally life-changing experience. For the staff, there's lots of evidence that we've infused new dimensions of diversity awareness, provided collaborations, and people have told us that they've been able to, to expand their research portfolios through this program. So next, I'm going to talk just briefly about the broader engagement program that we organize at SCIAM CSE. And the idea of this is, again, to work with these unusual suspects, bring them to the conference, infuse them into the community and the professional society. But we're also working with the broader community to try to, again, do what I call is normalize inclusion. And that is to create environments, give people opportunities to learn how to create environments that will be more inclusive. So when someone participates in the broader engagement program, they get full access to the CSE conference as well as travel support. And then we organize a variety of special activities. The first one I'll talk about is called the Guided Affinity Groups. And that's something that has matured over the years and has really become a kind of a cornerstone of this program. And the idea of this is that we develop small learning groups. So we take all the participants and we break them up into even smaller groups. We invite volunteers from the society to lead the groups. They meet once virtually prior to the conference, and then every morning before the conference over breakfast, they get together and they talk. The leader will suggest sessions to attend that day, answer questions, help them prepare for the required presentation at the end of the week about what they learned. And then many of the leaders will do a lot of extra in terms of helping the students network and do other types of mentoring activities. There is a formal mentor protege program as well. As I've already talked about the D&I panel, we usually try to organize. We do a lot of community building. We give the participants the opportunity to present their research either in oral or poster format. We organize tutorials and a variety of professional development activities. So next, I'm going to talk about a few stories of people who've gone through these programs. Of course, the first one is Derek Jones, who you've already heard about from the panel. So he was a master's student when he participated in SRP. He participated 2 years in 16 and 17. His mentor was Bert DeJong, and he was there with Sally Ellingson. And then the following year, both Sally and Derek went to Lawrence Livermore Lab to do an internship. He presented his research at BE program in CSE 19. He's now currently employed full-time at Livermore, and he's also recently enrolled in a PhD program at the UC San Diego. And then we have Rafael Zamora Resendez. He's from Hood College, which is a very small liberal arts college in Maryland. And he had just finished his bachelor's degree when he participated in SRP summer research in 2017 with Sylvia Crivelli as a mentor. He was hired directly into a full-time research position, and he's still employed there. He's presented his research at SC, at the Rocky Mountain Bioinformatics Conference, and at BE. And he's believed to be an outstanding researcher. Literally, the staff were fighting over who gets to hire him. He's believed to be worthy of the CSGF program when he's ready to pursue his PhD. Another person who's been kind of an alum of our programs is Alexandra Ballo, who's from Youngstown State University, which is in a very, very economically challenged area. She's a first-generation scholar from a rural farming community. She never would have kind of ended up where she is now without access to these programs. She conducted research in 2018 in John Wu's group as an SRP student with her faculty member. She presented her research at 19, and the pictures here are of her. She took advantage of a workshop we have to prepare people for this, and then she presented her poster blitz in front of 1,000 people at SIAM, this little young undergrad. She's so brave. And then during the BE program, her guided affinity group leader was Ann Almgren. And so she returned to Berkeley Lab the next year to work with Ann, and she presented her research from that at BE this year, and she was just awarded CSGF. And if you want to learn more about her, there's a link here to a blog post on the BSSW Better Scientific Software site, and you can learn about more about Alex and some of the work that I'm doing as a fellow of BSSW. We have Dan Rosa from the University of Puerto Rico, Mayagüez. He was a master's student, and he worked with Sylvia Crivelli as a mentor in 2018. He subsequently was awarded a GEM scholarship to support his doctoral work at UTEP. And then, so he did his doc work at UTEP and did summer internships at PNNL, and he's now a full-time data scientist at PNNL. And then here's Bryce Kroenke from American River College, which is a community college. He's a first-generation scholar. He worked with Sylvia Crivelli in 2018. Later that year, he presented his work at SC, where he met people from Oak Ridge and was invited and accepted into their artificial intelligence summer internship program. He gave an oral presentation at BE at CSE 19. He transferred from American River College to UC Davis, and he completed his bachelor's degree in 2020 and now works as a solution architect at Dynamics. And then we have Elise, who's from Pacific Northwest University, or sorry, Seattle Pacific University. She was a third-year undergraduate when she worked with Ann Almgren in 2017. She went on to complete her applied math master's program at University of Washington, and she now works as a data scientist at PNNL. So she, just as a note, SPU has about 70% female population and a very large URM population as well. Courtney Schaefer was a post-bac fellow at Berkeley Lab, she, under the direction of Dan Martin, she presented her research at BE this year, and she's a co-author on a Nature paper with Dan, and she also was just awarded CSDF to attend the University of Buffalo. And this was the first time she had ever presented at a conference, so we were delighted to be able to help her kind of make that process a little easier. And then we have Victor Zendejas Lopez, who is a UC Berkeley undergraduate who worked with Ann Almgren. He was presented his research as part of the BE program and participated in BE this year. Is currently serving as a co-mentor of two current SRP students that are working at the lab this summer. And he also was just awarded CSDF and is heading to Caltech this fall. So just to summarize, kind of what we've learned is that being the first and or the only one of a particular group comes with some challenges. And those challenges might be hidden, or they might be things that others just take for granted. However, there is a lot of unrecognized talent out there. You have to find them, and then you have to support them and give them the opportunities and the resources so that they can succeed. While organizational change may be very, very slow, dramatic shifts are possible, and it takes diversity as well as inclusion to achieve the goal of equity. And it's most certainly important to have advocates, and they don't have to look like me, but we really need to have those opportunities and resources to make a difference. So that concludes my slides, and I'd be happy to take questions if there's times.
Absolutely, questions. Roscoe, then John, then Bruce.
Yeah, well, thanks, Mary, and congratulations on your successes and approach and all that you've done. One question, a couple of questions, but one is, to what extent do the folks who you're working with interact with each other after they pass through the program? Are there mechanisms set up that do that, that help them do that, or are they all sort of each independently following their trajectory through the world?
Yeah, that's a great question. So we do what we can with the resources we have to try to foster ongoing relationships. And really what we hear from people that come out of these programs is that they develop what they consider are going to be lifelong friendships and relationships. And so we try to connect them through all the various sources to help them keep connected. Yeah.
And I know you're working with particular labs and so on, but how would you envision these activities scaling up?
Well, they can scale. So the broader engagement program has already, grown significantly. And we've been asked by SIAM to, they love this program. So they've asked us, we're doing it just at CSE, so it's every other year. And they've asked us to expand to other conferences. So that's one way we'll be scaling. And then we also can scale that up to larger. We've also been approached by some other labs to try to do SRP at other labs. So we've looked at that as well. So I think that there'll be some challenges, but I do really believe that this can be scaled.
Okay, thank you. I guess I was going to ask last, when's your estimate when some of these folks will join us on ASCAC?
Well, hopefully not too far, We have people in CSGF. We see CSGF as a pathway to ASCAC for some. Yeah, absolutely.
John, thanks, Roscoe.
Marianne, just like to second Roscoe, great program. It's really great to see the success and the number of people that have been involved with this that have turned into CSGF fellows is really remarkable. One question I had, I made note of the number of the high percentage of first generation scholars in that program that you had. That's pretty unusual in my experience for programs like this. And so I was curious to know whether or not there were particular things that you did there in terms of outreach, just to make people that, in communities where there's a high percentage of folks that like that, perhaps community colleges or whatnot, where you made real efforts to advertise the program. Was there anything in particular that you did that might have translated into that, such a large percentage of your students being first generation scholars?
That's a great question, John. I think there's kind of two aspects to it. One is that we absolutely did in our outreach intentionally reach out to places where we knew we'd find these unusual suspects, as I say. The other thing that I think really made a huge difference is that it's on the other end, is that the way we define diversity is we include first gen scholars. So a lot of programs don't consider first gen as a difference, and so they don't get a point. So I'll be really frank here. We have white men who come through the program, but they're first gen scholars, and they most certainly need the assistance and help. And it's really, I think it's more attributable to that. I mean, the outreach is there, absolutely. I can tell you there's plenty of people out there that are first gens that are very talented, but I think the real difference was on the other end.
Great, thanks. And one question around, with regard to Roscoe's point about scaling. One thing that we've seen here is that we've had a lot of luck in these programs, rather than having a one-on-one matching mentors to teams of students, and actually building projects with teams where there's typically a mentor, there might be a postdoc and a grad student that's overseeing a group of undergrads. And that's a way to really, both scale things up, but also work within a framework that's much closer to the way that people tend to work at the labs. So just a suggestion to think about.
Yeah, absolutely. And actually, I think that's a lot kind of the same idea that we kind of try to use with those guided affinity groups at the conference. So there's kind of one mentor and they've got a dozen or so kids with them.
Great, thanks.
So yeah, thank you.
Yeah, I think I'm next. Marianne, this is really important work. Thank you for everything that you're doing. A simple question just reflects my own ignorance that I hope you can answer. If not, maybe someone else on the call can. Does DOE collect and report diversity statistics on their grant recipients?
I'm not able to answer that. Maybe someone from DOE can answer that.
Dan, do you know?
I don't off the top of my head, no. I do not know the answer.
So I really appreciate that question, because we believe that one of the most important things, first of all, is to have the data and to know what it looks like. So we have worked with a couple of the labs to look at some of their data and try to compare that to the supply and try to provide some suggestions on how to address it. But data is the first place to start.
Anyone on the call know the answer?
Yeah, I see Christine's got her hand up. Maybe she knows the answer.
Yes, the PAMS system that collects this sort of information. Currently, the demographics module is dimmed, but we are in the process of going through the internal and external review processes to turn it on. So the answer, unfortunately, is at the moment we do not collect that demographic information on our grant recipients, but we are in the process of changing that and beginning to collect it on a voluntary basis.
Thank you, Christine.
Bruce, were there other things, or should we go on to Martin?
That was it. Go on.
Okay, thanks, Martin.
Great program, fantastic work. Interesting that you recognize first generation scholars. That resonates personally with me in understanding their challenges. I had a sort of question with regard to the comment that you made about strategic versus sort of tactical hiring. You know, in some sense, what your program has done is enabled people to acquire sort of, you know, metrics of ability in some sense. But in a more general setting, how does DOE recognize potential when those conventional metrics may be missing? And, you know, are there any more fundamental changes that should be made based on what you've seen from your panel and other members and your experience with the people who've come through your program?
So how does DOE recognize the metrics? I think
recognize potential when the metrics are missing, or only partially there, or correspond to things that are done in much more challenging situations.
Right. Well, from my experience, you know, I think that what's happening through these programs that we're seeing is that we're widening the aperture, shall we say, so that people can start looking through at changing the metrics, basically. So where in the past, maybe someone was, you know, I have to have someone exactly with this, you know, specific, you know, technical skill. Well, maybe people are realizing that you can get the talent and you can develop them so they're capable to conduct that research at the time when it's needed.
Thank you, great answer.
Mm-hmm.
All right, thank you, Marianne, for this thoughtful presentation. There's more work to be done in this space, without doubt. So thank you.
Sure, thank you for the opportunity.
All right, next up, Katie and Susan are going to give us an update on the Exascale project.
Okay, great, thank you. I think it's just me today.
Okay.
Susan had a conflict, so let me share my.
I see Susan, Katie. We also don't have your slides, so if you could be sure and post them in the Google Drive when you get a chance after the talk.
Yeah,
of course.
I will post those afterwards as soon as I can here. All right, now I'm going to go into a presenter mode. How does that look for you? Do you see the full screen or two screens?
Nope, it's good.
Okay, great. So yeah, thank you for having me here today. I'm Katie Antipis. I'm the Hardware and Integration Director in ECP, and I'm from Berkeley Lab and work at NERSC with my other hat on. I think this committee is really pretty aware of the three technical areas within ECP, but I wanted to highlight for any new members that hardware and integration, we are one of the three pillars within ECP, along with the application development area and the software technologies area. And our key goal, if you ask me what is our key overarching goal in the hardware and integration area, it's really to assure that the really enormous investments that are being made into these exascale systems and to the applications and the software can be realized in practice by our users and for the long term. And so what we're focused right now heavily on in hardware and integration is helping those application teams get their codes tuned and ported for the exascale environments, helping the software teams get that software deployed onto the exascale platforms so that the software can be used by the broader community, and then training the community on how to really use these systems. We have a really fantastic team. My partner in all of this is Susan Coughlin from the ALCF at Argonne. We're talking every day, multiple times a day, as part of the ECP project. And then we have 6 what we call level 3 areas under the hardware and integration place. 2 of them are really focused on hardware, and those were path forward and hardware evaluation. Those 2 areas are in path forward, in this case it's actually wound down, it's closed, and hardware evaluation is coming towards the end of its sub-project. And then Scott Parker leads our application integration area. Ryan Adamson leads software deployment. Haritha Siddhartha-Nisom leads our facility resource utilization, and Ashley Barker from the OLCF leads our training area. And so you can see all of these leads here, we're actually facility staff. So we work really closely with facilities. We are the Oscar facilities, and so we really can facilitate that communication from ECP back and forth between the facilities. I have never presented to this committee before as part of ECP, and I've been in the role for 15 months. So I think the last time you heard an hardware and integration update was about 18 months ago from Terry Quinn. So I really wanted to highlight in this talk what has really happened in that time frame, what's happened in the last year. And I think the big thing I would highlight is we have hardware, and that is just huge, because that makes what we're doing so much more concrete. When we have some early hardware on the floor, then the application teams and the software teams can really get on that hardware and start to test out the software environments, even if the hardware environment isn't in the final stage, which of course it isn't at this point. But so this has been a real focus of what we've been doing in the hardware and integration space. So our application and integration teams are really working closely with those 80 teams to get their codes ported onto that early hardware. We're testing our software deployment capabilities on that early hardware. And we really converged around E4S as a vehicle. So I'll go into that later. Our training and productivity areas have really sort of shifted to focusing on the hardware and the platforms that are coming in. And we're certainly tracking very closely the Perlmutter deployment at NERSC. So that is identifying a number of system software and networking issues that are really serving as a risk mitigation for Frontier and Aurora. And then I think I'll note as well that our path forward area did recently close out, and we did achieve the stretch goal there for the project in terms of the number of vendor milestones. I thought I would take a minute or two to walk through this slide in some detail, because it really is the hardware that we deploy really drives what we do on a day-to-day basis in hardware and integration. So the bottom right hand corner, this is sort of the schedule and the timeline for the exascale system when ECP users will get access to the exascale systems. I'm not able to share the Aurora dates with you right at this point. They're not publicly available, but you can see the Frontier dates. And so if you go up back to the left on this graph, what you'll see is all the early hardware deployments that our ECP teams have had access to. And each one of these really serves a different purpose, and it also serves as a risk mitigation because we use these systems to find bugs in the system software, to find bugs in our own codes, to see where there may be areas where we can increase performance. And so right now, the stage where we are at is these early access systems. They're named Arcticus and Spock. I did not name those, but those are where we are right now. And so most of the teams, they're getting on those systems. They're doing single node tests, functionality tests, early hardware tests. And then each system that's kind of deployed after that gets closer to the hardware and the software, final software configuration. Let's see, the Frontier Test and Development System, we expect to come online for ECP users in the next couple months. And at that point, that is one cabinet of the final hardware and software. And so at that point, users will be able to do some multi-node tests, get on the final hardware. And finally, we'll do the full KPP demonstration on the full exascale systems, hopefully later in FY22. Here's a little bit more about some of the early access systems that we have at the OLCF and the ALCF. So at ALCF, the system is called Arcticus, and it's 5 nodes of the latest discrete Intel GPU. And the way that we support users on this system is through Slack channels, Confluence documents, email lists. We have about 150 users on the system at the ALCF. And then at the OLCF, one of the systems available is called Spock. It's 12 nodes with 4 GPUs of the MI100 AMD GPU. And so this is run by the OLCF staff in partnership with HPE. And this is actually new. It's available to all ECP members, and it's not under NDA. And so that has actually really improved the type of discussions that you can have when there's not any NDA restrictions. We also kind of track the usage, though the number of node hours that people use isn't really the key criteria here. It's getting users on, compiling those codes, finding issues, reporting bugs back. I'll also note that we do have some other hardware as well. These are the 2 of the latest that I'm highlighting, but there's remote systems that some users can access. There's systems that are run by the vendors that can be accessed as well. So let me move on to application integration. So the goal of this area, and it's led by Scott Parker and Balint Ju, is to really make sure that the application development teams are prepared to run on these exascale systems. And the way that we do this is that ECP supports these application engineers, the application performance engineers at the facilities. And so the 3 leads are Chris Knight, Stephen Nichols, and Debbie Bard from the ALCF, OLCF, and NERSC. And so these performance engineers actually sit within the facility teams and work with the facilities application performance engineers as well. So when you take a look at this team, it's an incredibly impressive group. I mean, I think we can describe it as just a small army of performance experts here that I don't think is unique probably across the entire US and likely the world. I think this is absolutely a best practice. The type of work that these engineers do span everything from identifying performance issues, working on programming models, optimizing algorithms, sometimes even on algorithm development. And I think what is particularly unique and a best practice for an application integration is that I consider it like a clearinghouse between different domains. So where else do you really find a group of performance experts where you find an optimization from a chemistry code and that knowledge can get passed back to kind of an astrophysics team? And I think to me, that's a way that we disseminate and distribute best practices, across, all of Augsburg here in terms of performance. And so these teams are really incredible. Okay, keep moving forward here. So we just finished a recent milestone report in the application integration and also the software deployment areas. And the current report is under NDA. However, the team is looking to see if there's options for a public release next year, particularly as some of the hardware comes out from NDA. But what was really called out in this report was just how crucial the application engineers have been in helping these AV teams really interpret performance results, make productive use of the early hardware, and also, because these teams live within the facilities, they have the relationships with the vendors and they can advocate and articulate for certain issues that that need to be fixed. So I think we've reported over like 100 bugs or issues as part of this application integration team does. And really, the sooner that we identify issues and bugs, the easier it will be to demonstrate the KPPs on the full scale system. I wanted to walk through a couple of exemplars from our application integration team here. This example is from the games code, and the credit goes to Colleen Bertoni from the ALCF. And so, games is a quantum chemistry code, and they were looking to move this particular kernel from a CPU only version to GPUs. And so if you look at this graphic here on the right, you can see a progressive set of optimizations, starting with version 0.0 here, which is a CPU only version. And then OpenMP is added in version 10. And then MKL is integrated, and you see a big performance boost to version 20. And I asked Colleen, so what happens between version 20 and version 30 here? And one thing you could call it as well, maybe I shouldn't read that much into it because you're actually going to a different set of hardware. The Intel Gen 9 is an early, GPU. But I think what Colleen noted was that the first port to a GPU is sometimes not the most optimal. And so if it's a simple port or a naive first try port, it often takes further optimizations to get performance out of these systems. And you can see that in the improvements in the 45 version and the 50 version. I think another thing that we're seeing across that's pretty common from the application performance engineers is that it's not really just one optimization that sends you from 0 to 100, but it's a succession of smaller optimizations that altogether is what's creating the large performance improvements we're seeing out of these teams. The next application I thought I would call out here is from our Exabiome team. And this was a really interesting piece of work because Exabiome is looking at assembly of metagenomes. And this isn't traditionally very easy on a GPU. And so in particular, some of the graph traversal methods just are not well suited at all. And so this team was looking at really low level intrinsics in CUDA in order to get a speed up. And then they ended up getting a pretty magnificent speed up, about 7x faster than a CPU only version on Summit. You can see as it scales out that it becomes more communication bound, and that difference is not as great. But I thought I would call this one out because it does still demonstrate that performance portability can be a challenge, especially in some of these type of algorithms where teams are going down very low into use intrinsics. And so the team is looking, to do that same type of work for the AMD and the Intel GPU as well. This team also got nominated for best paper in SC21, so we were really proud. Then the last application I wanted to call out was NWChemX, and this is an incredibly popular application that's been used, on our supercomputing systems across ASCAC for a long time now. It's a big and complicated code, and so what this team was looking at is the key challenges were to get a GPU version, to get some performance portability, so this code could run across multiple architectures. And then I think there was a lot of challenges with data movement between the nodes as well as on the nodes. And so this team has introduced a portability layer, and now they have backends for each of the three, or they have backends for the NVIDIA and the AMD GPU. And what you can see is a pretty incredible performance speed up when they actually move on to the GPU. And so in this case, it's about a 40x speed up if we look at kind of the difference between this original blue bar down here on the right and then this yellow bar. I think the feedback and the impact that the application engineers that have been having in on the application teams has been really great. That we had a number of comments in our reviews that said, well, it looks like you're doing a good job with the application teams. Is there anything AppInt could do to support software technologies? And so we took that feedback, and so we have recently increased support for the software technologies teams as well. So I think it was about 18 months ago, right before I started, ECP was supporting some work with the AMD, Intel, and HPE engineers to help look at some of these software technology libraries. And then just this last quarter, we've also added some software technology support for more math library engagement from the application engineering team, for HDF5 and IO support, some more support for COCOs. We also have some more support for ST teams at the OLCF from Tom Papatheodore to do some deeper engagements with those teams. So this is just launching, and hopefully we'll be able to report back to you on progress there. So let me move on to the work that we're doing with in our software deployment area. So the role of software deployment is to take the very large number of packages that are being developed by our software technologies teams and to get these deployed, installed, and compiled onto the exascale architectures. So this is a really large number of packages here. And I think our challenge was how are we actually going to do this? How are we going to engage with these teams to get these teams, to get all this software onto the systems? And so I think we've come a really long way in the last, what happened? Am I still here? Oh.
You're still here.
I'm still here.
lost
My
your slides.
PowerPoint is not. Okay, it says PowerPoint. Sorry, let's see if I can do that. Okay, hopefully I can just go back again. All right, I think we're back. Okay, so with that pause, so I think since the last time we've reported back to this committee, we've come a long way. We've also made a number of changes in this area. So if you look back about 18 months ago or so, and in our last review, the review before last in December 2019, I think that we just transitioned our leadership to Ryan Adamson at the OLCF, and I mean, I think some of the feedback we had was that we had a strong vision here, but we didn't necessarily have a clearly articulated plan that could be easily understood. And so where are we 18 months later? So one thing that we've done is we broke apart the continuous integration area and the software integration area. I mean, this is a little bit of a project management speak, but we realized that we could probably better make progress by separating these two areas, because you can work on deploying the software without automating it, and you can work on the infrastructure to automate that deployment without the actual software there. And so I think that clarity has actually helped us. The second key thing that we did that was probably the most significant is that we made the decision to leverage the E4S software stack, and more importantly, its packaging, to significantly simplify our deployment and continuous integration plans. So E4S requires that those teams build a stack package, make a recipe, and in the software deployment area, we can take those directly and do our installations onto the systems. And this has really been huge, because instead of interacting with 67 different product teams, we're now working with the E4S team primarily. And then, you know, as necessary, we'll go out and work with individual ST teams as well. So we have E4S pipelines with continuous integration now deployed on the production hardware at the facilities. And sometimes I've been asked in reviews, well, why are you doing this on the production hardware? And our answer is, this is really new for the facilities. And so we have to sort of practice this. We can't, the first place we do this can't be on the exascale systems. And so we have pipelines on the Cori system at NERSC, on the Ascent test and development system for Summit at the OLCF. And then we are tracking our progress closely, holding ourselves, you know, accountable. And so you can see some numbers down there at the bottom. Right now, our goal is 67. Sometimes more packages get included in E4S so the denominator can go up. But you can see, you know, we are making steady progress in getting these packages ready to be deployed on the systems. And so again, this really simplifies our deployment plan. You know, I think maybe 18 months ago, we were down at the bottom thinking that we would be engaging with each individual ST team. But now these packages, these software packages are part of SDKs, and then those SDKs become part of E4S, and then we can operate at that higher level and deploy that E4S as a package. Okay, I think I have a couple more slides here. I did want to call out some work by our hardware evaluation team. Their work is, they're writing up some kind of final reports right now, and this is the type of work that they do that I think can be really impactful for OSCAR as we're thinking about the next generation of systems. So this team, Ivy Peng and some colleagues at Livermore, were looking at a study of, you know, excess data movement. And you know, why is this so important on GPUs? One, because it's expensive to move data. And two, a lot of the teams now are trying to keep all their data on the GPU memory and do their calculations there. And so you want to look at, you know, are you moving the data you intended to move? Are you moving more than you thought more than you needed as well? And so, you know, this is a study this team did looking at this XS bench kind of kernel, and was able to see, you know, the amount of data used was very different from the amount of data that was moved. And so they've created some tools that are related to, you know, being able to note and see this excess data movement, and identifying kind of what cases or what type of calls that may be made that would lead this to happen. And then I think finally here, I wanted to just talk a little bit about our training area. The ECP training events have been popular for the entire program. And so we recently had our annual meeting. There was about 30 training that were there with really high numbers of participants. It's been interesting in this remote environment because I think, you know, the facilities we used to put on our own trainings, but now that everyone is primarily in this remote environment, a training put on by one facility or another, you know, doesn't really matter as much when everything is remote. And so this is something I think would be really fantastic to keep going after ECP. Is so thinking of like an Oscar-wide training programs. I think we can cover more topics, we can reach more people. And in some cases, like this upcoming CMAKE training, a number of the facilities are actually collaborating with ECP on it. Okay, so in summary, I think hardware and integration, we're really excited about the hardware that's coming down the road here in a few months. And I think that the hardware and integration team, we're really prepared to help with the problems and challenges that we know will come up when you deploy the first of a kind systems. And so we really have that frontline team of application engineers that are going to be able to help identify issues and bugs, find areas that they can improve the performance on the codes. And so, you know, we're excited about that. We know that's also probably our biggest challenge going forward, is that these are new systems. When we talk about, you know, the scale testing for Frontier, it is Frontier, right? There's going to be no system that has been tested at that scale. And so we certainly are expecting that there will be bumps, but we think we're prepared to help and to expose system issues, to help harden the system, to help improve these application codes. And so I think the next year is going to be really, really fun and exciting for hardware and integration. And you know, I know the teams can't wait to get on these systems. So I think that's all I had, and I am happy to take questions.
All right, thanks, Katie. Are there questions? All right, going once, twice. All right, thanks so much, Katie.
Okay, thank you.
So as you know, we're running a little behind, so I'm gonna exercise chair's prerogative and make a runtime decision here. And what I would suggest is that we just press on and people take a break when they need to. Just turn off your screen, go do what you need to do. But why don't we just go ahead with the next presentation, and we'll just press on from there. So next up is COVID-19 S&T response, the National Virtual Biotechnology Laboratory, and Michelle is going to make that presentation. So Michelle, floor is yours. I don't know if you're muted. We can't hear you.
There we go. Again, we'll try again. I really appreciate the opportunity to represent the work of several hundred members of the NVBL team. And I hope by the end of my presentation, you can see the great impact that this team has had. If I can have the next slide. Looking at the Department of Energy, one wouldn't think that we would have much of a role in helping solve the COVID-19 crisis. But if you go back in history, the DOE has been deeply involved in biology since its very origin, when the national laboratories looked at trying to define the genetic defects that occur upon radiation. And over the years, that has just increased in many different ways, including the DOE's involvement in the Human Genome Program and developments that have impacted modern biology, including the CRISPR-9 technology that won the Nobel Prize a couple of years ago. So we have a very deep resource within the national laboratories of scientists and engineers who have expertise. and actually capabilities at the facilities that DOE sponsors for looking at things like analytical technologies and trace detection. So some of these technologies that you may be aware of are things like genome sequencing tools that were developed, or even proteomics tools that have been developed. A lot of work has been done on the computational aspects and the structural biology aspects, which I'll talk a little bit more about, for discovery of antiviral drugs and vaccines. And of course, looking at manufacturing technologies, modeling, and other aspects that we were able to bring to bear. But first, I want to talk about the user facilities that many of you know about. And in the next slide, you can see you guys know a lot more about this than I do. And I'm kind of talking to the experts here, but this high performance leadership computing facilities play very heavily, not only in the MDBL, but also in providing these very valuable resources to the greater biological community and the biomedical community. And Barb has told you before about the COVID-19 HPC consortium, of which DOE was a primary member with other countries and industry and academic members who opened their capabilities to the greater scientific community. But specifically in the NVBL area, looking at protein molecule docking, especially doing a very quick scan of existing drugs to see if they had efficacy against COVID was very important. Developing antibody type treatments, and then looking at pandemic modeling and modeling in fate and transport of the virus in buildings and transportation venues. So there was a lot of involvement in computing that really enabled a lot of the work in NVBL and the product that was delivered by the department. May I have the next slide, please? So light and neutron sources, as you probably are aware, they are real power horses, workhorses for determining structure of proteins. And when you look at the 5 light sources and the 2 neutron sources, a lot of the work going on there is looking at structure of proteins, and this is a very important part of NVBL. Also looking at other mechanisms, for example, of how the virus interacts with the membrane and actually enters the cell, and looking at dynamic studies of drug and antibody interactions as we try to predict and then demonstrate the interactions with trial candidates. And the next slide. And even our nanoscale science research centers were important players for the user facilities. Again, all 3 of these types of centers were open to the general community. And so things like looking at small molecule synthesis, once computational tools identified good candidates for testing, many of these small molecules were synthesized at the Nanoscience Center. Sometimes they were deuterated for studies with NMR or neutrons. Things like cryo-EM were used to look at proteins and protein complexes and so forth. So these nanoscience centers also came into play. And it was really great to see the type of access that the CARES Act, this was funded, provided to keep things like the computing centers, nanoscience centers, light sources open during the pandemic to get access to the general community. And this was an important part of DOE's contribution. Now, if I can have the next slide, please. So the NVBL was work that was done on top of the work for the nanoscience, on top of the work for COVID. And this was initiated in March of 2020. And again, it was funded by about $40 million of the CARES Act funding. And this was stood up very quickly to have a kind of a whole is greater than the sum of its parts approach to looking at things that the Department of Energy National Laboratories could actually do to attack the problem of COVID. And so this started out with an executive committee that included 3 members from national laboratories, and that was Steve Streifer from Argonne, Marianne Walk from Idaho National Laboratory, and me when I was at Oak Ridge. I'm on assignment now to Harriet Kung's office. and then Harriet Kung and Ashley Predith out of the Office of Science. And as an executive committee, one of the first things we did is we interviewed and discussed with other agencies where the technical bottlenecks were that would be something that the department could address. And so we reached out to the 17 national laboratories and the chief research officers and looked at capabilities that they had at their laboratories and see where those capabilities matched up with the needs of the broader biomedical community. And we set up 5 different areas, which I'll explain in just a minute, where we focused on. And we divided these up into 5 teams, and these teams were told, get together, take your best ideas and go for broke on these, really having sprints that were weeks to maybe a couple months long to try to develop technologies. These were research projects, but they were very focused and there was a high degree of urgency that were put on this. And it was really wonderful to see how some of the people that were working together hadn't even met each other and across the 17 laboratories. And to get this group of very talented people to set aside their own research programs and to pull together and solve these problems was truly a classic case of the national labs working together and solving problems for the nation's benefit. And in addition to looking at the national laboratories, we also worked with universities, private industries, other federal agencies. I'll tell you a little bit more about that. And we also supported decision makers at the local, state, and national level. So there was quite a bit of effort that was put into that. So may I have the next slide, please? So again, I'm going to do a little bit deeper dive on the 5 topic areas, and they're listed here on the left, but I want to draw your attention to the right side of the slide. In the background there's the web screenshot of the website that is on the web, the NVBL, and you can find that. And inside there's some information and some other other websites that you can go to. One thing in particular is this red booklet up front, which was a summary of things that the NVBL had done as of, it was about February. And we are updating that now that the funding is coming to a close on NVBL, and we'll have a final report posted there. But there's some very interesting stories about the capabilities and the accomplishments of the NVBL team. If I can have the next slide. This is kind of a success in a nutshell slide, just to show you some of the impacts before I go into detail. Again, we talked about the user facilities, very much a critical part of looking at the structure of the virus, and it supported vaccine development in all 3 vaccines that were used in the United States. And Pfizer actually calls out the fact that they got critical information from the light source at Brookhaven. And so it really did have a big impact on vaccine development. Other things that we did was supported CDC, FDA in testing. And so when the test kits were first brought up, they had to develop the test, clinical test for COVID. A lot of things came onto the market in the United States, both domestic and foreign produced test kits. And CDC and FDA looked to the laboratories who have a long history in analytical methodology to verify the efficacy of these tests. And actually, we found a number of tests that just gave too many false positives and false negatives due to contaminants. And so that was another role that we had kind of outside of the R&D side. Again, talking about computationally screening billions of compounds against virus targets. I'll tell you a little bit more about that. And also looking at X-rays again and neutrons. One thing that I'll talk about is providing critical supplies. And one of the things that was very exciting about this is that the laboratories had contacts that they reached out to and in industry, and industry actually started producing these materials that were in short supply and created hundreds of new jobs. And then finally, this is another feather in the cap of our computational colleagues. I'll show you the slide up top shows an area that was really looking at transportation into and out of the Chicago area. And some of our modeling technologies were able to look at predictions of what would happen if transportation slowed down, if people open bars, close bars, open schools, and try to look at the impact. This particular case is in the Chicago area, but I mention it because just today we heard that some of our team members at Argonne were recognized by the governor of Illinois for helping them do work both locally in Chicago and in the state of Illinois to model the spread and impacts of both administrative and engineering preventions for COVID spread in those areas. So a lot of good stories that have come out of that. And now I'm going to drill down a little bit to tell you some other details. Next slide, please. So advanced manufacturing really took advantage of a lot of the materials capabilities that are resident in the Office of Science, as well as the Advanced Manufacturing Office in the EERE side of DOE. And before COVID broke out, there was and still is, a very large facility that is developing low-cost carbon fiber. And during the COVID outbreak, you are all aware of the fact that N95 masks were in very short supply. And there was a lot of worrying about, having to, sterilize them, reuse them, et cetera. But the fact is that the supply coming into the country just wasn't sufficient. There was not enough manufacturing capability in this country to meet the need. And so the people at the carbon fiber facility, as well as the NVBL team, turned around and started doing melt-blown polymer media development so that they would have this very fast way of making these new polymer materials for test. And the other thing that is very important, and you may have read about some of the masks that came into the country were not legitimate. The problem that they had is that they did not put a charge on this material. And so in these filter masks, you have the polymer that has the ability to filter out larger particles. But the secret is that the smaller particles have to be removed from the air that you're breathing by electrostatic charging, okay? And this has to be something that is semi-permanent in the material. And without that charge, the most troublesome materials actually pass through the mask and go into the lungs and cause problems. So that charge has to be there. So working with the inventor of the N95 media, who retired from 3M many years ago, we developed a way to adapt this charging device to any product line that can make this type of filter media. And so a lot of work was done at the X-ray centers and nanoscience centers to test these materials to verify the efficacy of the filtering. And then we reached out to some contacts that the laboratories had with Cummins Diesel, of all places. It was kind of an interesting place to go. But Cummins makes diesel engines, and they also make the large air filters that they use on these diesel engines. And they had production facilities where they were making these types of filter media for their engines, and they converted their facility over to making this N95 media that had the appropriate charging mechanism to have validated effects. And then after that was done, they went to a small company called Dematec in Florida, and they set up production lines, again, helped by the NVBL team. And now they have 3 production lines that are making millions of masks a week. And they created over 600 jobs. And NIOSH certified those masks for use in October of 2020. So it's a really good story. The next slide. Another part of our advanced manufacturing team looked at sampling kits and other medical supplies that were in short supply. You might recall they ran out of swabs. They couldn't produce enough swabs. There was only one company in the United States that made these swabs, and they team out at Lawrence Livermore developed the use of 3D printing to make swabs, enabling the production of 300,000 swabs per day per machine. And further, the picture on the right of your slides, you may see that there's a little logo there. It's a little small of Coca-Cola. We worked with the Coca-Cola company. They have these things called preforms, and when they start making bottles to put soda in or put water in, that's how the bottles come. And they take that preform and they stick it in a form and blow hot air in it to make a Coke bottle or a Dasani water bottle. And so knowing these were about the same dimensions as the sampling tubes that were in short supply, we worked with Coca-Cola to ensure that the material there was compatible with medical sampling, and also develop sterilization techniques to be able to make these. Coca-Cola makes billions of these preforms a week, and they made one of their production lines available for making 2 million test kits a week. And then another type of tube that was developed, we did in conjunction with Thermo Fisher Scientific, and these tubes were difficult to make without new tooling. And so the labs came up with 3D printing of these tools. That's the middle figure there in your slide, and came up with that tooling that would have taken months to make and made it just in like a few days, and allowed Thermo Fisher to convert one of its plants in Lenexa, Kansas into production of these new tubes. And they ended up investing $40 million in that factory, and then also employing 300 new employees. So the next slide, please. So the testing and protocol group, they really focused in on helping the country develop better testing protocols. And you can see that the kind of end-to-end steps that have to be taken for testing of human samples. So collection and transport was one thing. Those of you who've had your nose swabbed, it's not the nicest thing in the world. And so they were looking at alternatives to nose swabs. And one of the things that they evaluated is a little physical device. It looks like a whistle. And when you blow into it, it actually has a whistle sound. And depending on the sound of that whistle, you can time both the length of time needed to collect enough sample, but also how hard you're blowing. And inside the whistle, there's a little sorbent material that can be removed, and just like the swab material, it can be tested. So it's a less invasive sampling test. And so that's going on to further test for not only COVID, but other sorts of respiratory infections. Another thing I'll draw your attention to is down here on the lower right side of your slide. There's some new detection technologies that are being developed, and this is a prototype of a microfluidic device. And what this is trying to accomplish is to be able to test for not only COVID, but for DNA from other types of infections that might be also impacting a patient. So when somebody presents themselves, the physician can do a test to see if they have strep or they have some other co-infection, and be able to treat the patient holistically instead of just trying to treat one particular infection. So the next slide, please. This is a summary of some of the approaches used by the medical therapeutics group. In this case, our team worked very closely with university researchers and researchers at NIH and also in pharmaceutical companies to do both the computational modeling, to look at docking, to do structural biology. And the whole concept here was to help expedite the potential drug therapies, therapeutic agents that could be used, both drugs and antibody type reagents. And so again, they looked at a lot of different crystal structures. As I mentioned before, billions of scans were done on small molecules, including all the known drugs that have been approved for human use, so we could look at that. And also, one of the things that happened here is because of our expertise, some NIH came to us to evaluate tests that some drugs were announced publicly on the open press about being able to reduce severity of COVID and things like that. And one of the things that we did was do some structural studies to try to give some insight as to whether or not they had any chance of working or not. And so that was another resource that we served for NIH and FDA. But one of the things that is very important in looking at all this is that in addition to looking at protein docking with the COVID proteins and drugs, that docking is necessary, but it's not sufficient to be a good drug. And we also developed computational models that would allow not only to look at that docking, but to understand the probability of the activity of the drug and the ability to have the desired biological effect, but also to understand if it had the potential to have good physical and safety parameters. So all of those have to be weighed in. And the team that we have right now have identified a handful of very high probability candidates that have moved now into university laboratories and even pharmaceutical laboratories to get into the chain for testing for COVID. And so that's ongoing work that will be continued. So the next slide, please. The DOE also has deep expertise in looking at fate and transport of materials in the atmosphere and environment, dating back to looking at radiation transport. Also pollutants in the air, in water, and on surfaces. And this is also reinforced by some of the capabilities that are available from the Building Technologies program within DOE, in which there's facilities at Berkeley, PNL, and Oak Ridge that are built to actually test HVAC conditions, building materials, and things like that. And you can see those figures on the left. What's very interesting is that you can reconfigure these buildings to mimic closed offices, restaurants. Here is, you can see the dummies sitting in open office spaces, and so you can test airflow and predict and model what kind of physical barriers can prevent the spread of the virus in the air and on surfaces. And so that was a lot of work done. Again, computationally very intensive, but also backed up by taking air samples and combining that very rich data source to predict how various administrative and physical barriers would impact the spread of viruses in closed environments. And if I can have the next slide. So finally, the last team focused on epidemiological modeling and logistics support. And this too is something that has been a long-standing area of expertise within the Department of Energy. And you look back in work done with the Department of Defense to look at logistics and shipping supplies overseas, looking at the response to the hurricanes. This was work that was done for FEMA and other agencies that, for example, you want to know how to get the population out of the center of New Orleans, the most effective ways, and which roads to close and which ones to keep open, how to get supplies in after the event. So this has been work that has been done at many of the national laboratories for many years. And so the epidemiological modeling group, again, developed these predictive programs that they modified for COVID, and some of them were very coarse-grained, and they looked at the United States and the globe and looking at predicted spread of the virus, but also there were some very fine-grained analysis where they could actually go down to the zip code level to look at movements within a particular zip code within a city to see what the impact was of a school opening, or what would happen if they changed the regulations for businesses being open or closed. And so a lot of this was done with close coordination with local and state governments. And I mentioned the work with the state of Illinois, but this was also done in New Mexico and Tennessee and many other states, and is still being helped today. A second area that they looked at was looking at resource demand and trying to identify where ventilators would be needed next. Ventilators were very short in supply, and being able to predict where those shortages were. Another thing is, what would happen if they had a blackout in a particular area? Where would hospitals be able to move their most critical patients, and economic impacts that came up from people being out of work. So there's a lot of modeling done in that. And then finally, the Vehicle Technology Office within the Department of Energy teamed with NVBL to look at the effects of transportation on many aspects. One was what would happen as the number of cars diminished, and it was extremely good, interesting data to see what happened of the number of cars on the street. And this is this slide here on the right, where you can look at what was happening about the number of cars on the roads. They also looked at freight movement and what was going to happen with supplies that would be available to commerce. So again, it was very multifaceted, the types of information that this particular team provided to many decision makers across the country. And then the last slide. I really can't get across the amount of impact that this group had. I only told you about a few of the results from this group, but this was really amazing to see people come together and work with people they didn't know for a common good. And it was something that the folks who did this were very determined to have the biggest impact that they could. The DOE has many capabilities, and the capabilities that we've shown now, I think that we could apply again to the next variant of COVID that's coming around, and also to other emergent diseases. But we've also, as a national lab complex, have come together to solve other crises that would include things like the Deepwater Horizon oil leak and even the Fukushima nuclear disaster. And I think the thing that is really important for people to know is this is really what national labs were created to do. Going back to the Manhattan Project, where we came together to solve a major problem, the DOE laboratories are asked time and time again to do this type of thing. And it's really a wonderful resource for this country to have in case of emergency, that we can come rise to meeting these challenges and bring new technology solutions to the community. And with that, I'll close and take any questions.
All right, thanks, Michelle, for that really broad summary of the ways that DOE has responded to COVID. Questions? Susan.
Hi, it's not a question, it's a comment. I just want to thank you, DOE, for all the work that you've done, particularly in the work of the HBC Consortium for COVID-19, as well as in the structural determination at the national labs. The work that you supported through those projects, many of those investigators were NIH funded, and finding the computational resources for their work is non-trivial in some cases, not in all cases. And so your ability to provide those resources that researchers could then very quickly reconfigure their research to address COVID-19 is greatly appreciated, and we did not necessarily have those capabilities at hand. So anything that could be done to continue that capability, and I'm happy to see that there's still projects being supported. I think the last one was in April through this consortium is just, really greatly appreciated, and truly thank you very, very much.
Any other questions or comments? Well, that's actually a quite good setup for our next discussion. So, Michelle, thank you very much. Appreciate it. As I said, we're going to just swing right on here and skip the break. Next up, Emily is going to talk about the collaboration between DOE, NNSA, and National Cancer Institute. So, Emily, over to you.
Great. Thank you so much. And thank you to Christine Chalk for inviting me to present today. I'm Emily Greenspan. As was just mentioned, I'm going to give an overview of our ongoing collaboration between DOE, NNSA, and the National Cancer Institute. I'm with the National Cancer Institute in the Center for Biomedical Informatics and Information Technology. Next slide, please. So the topics I'd like to cover today are a little bit about the collaboration background, governance and oversight, and then project-specific overviews, including our pilot on RAS biology on membranes, the pilot on precision cancer surveillance, a new project we are starting referred to as Innovative Methodologies and New Data for Predictive Oncology Model Evaluation, or IMPROVE for short, and then also ATOM. And then I will also touch on some of the capabilities, including models, software, and data sets that have been developed by the collaboration, and finish up with a few words about new opportunities. Okay, so the first, no, thank you. Okay, so a little bit about the history of the collaboration for those members who may not be as aware. The opportunity for DOE and NCI to work together came about in 2014 and was enabled by both the National Strategic Computing Initiative and the Precision Medicine Initiative. In June of 2016, the original 5-year MOU was finalized between the two agencies toward the goal of collaborative development of a shared technology ecosystem and targeted applications that will bring advanced computing capability to biological research and produce a transformation in drug and treatment development and ultimately patient care and outcomes. And then looking ahead to 2019, Pilot 2, which, as I mentioned, is focused on large-scale molecular dynamic simulations of the oncoprotein RAS on a realistic lipid membrane. A paper from this pilot won Best Paper Award at Supercomputing 2019. The paper was titled Massively Parallel Infrastructure for Adaptive Multiscale Simulations, Modeling RAS Initiation Pathway for Cancer. So that was a big benefit for our collaboration and showing the work that we could accomplish together in 2019. And then just last month in June of this year, we signed a new 5-year MOU that will automatically be renewed every 5 years to help promote a more sustainable and stable partnership. Next slide, please. So a little bit more background about the partners who were involved in the collaboration and history of the individual efforts that we've undertaken together. The major program under the collaboration is referred to JADAX4C for Joint Design of Advanced Computing Solutions for Cancer. The program has aimed to develop, demonstrate, and disseminate advanced computational capabilities that help answer driving scientific questions across different scales, molecular, cellular, and population in cancer research. These efforts are intended to frame forward-looking approaches for integrating and analyzing large heterogeneous data sets with advanced computational modeling that will hopefully accelerate precision and predictive oncology. As you saw in the brief history slide, the program is now in its 5th year. And in addition to the 2 federal agencies, we also are joined by 4 DOE national labs, Argonne, Lawrence Livermore, Los Alamos, and Oak Ridge, as well as NCI's FFRDC, Frederick National Laboratory for Cancer Research. There are also NCI extramural divisions and centers that participate. So on the right here is kind of a snapshot of the original 3 pilots that the collaboration undertook, or JADAX4C undertook. These pilot projects were defined by DOE and NCI leadership. And as I mentioned, they span across different scales or domains. These pilots also build on established national priorities that NCI has in understanding RAS-driven cancers, developing preclinical models, and building a network of cancer patient information. The pilots explore direction and inform future investments by using increasing amounts of advanced computing to accelerate cancer research. You'll also see there in the bottom right in the green that we've also, from the beginning, undertaken 2 cross-cutting technologies, one of which is Candle, which I'll talk more about a little bit later on, and also uncertainty quantification. And then, as I mentioned in the topic slide, there's also, in 2018, a public-private partnership referred to as ATOM, or Accelerating Therapeutics for Opportunity Medicine, was started, and that's aimed at using computational approaches in AI to speed up the drug discovery process. Next slide, please. Okay, so now I'm going to talk a little bit about the governance and oversight of the collaboration. The original governance and oversight structure for the collaboration consisted of 3 components. The FACA level oversight was under the Frederick National Laboratory Advisory Committee, or FNLAC. Since 2018, there's been a FNLAC working group that's overseen the collaboration. It was actually just concluded a couple months ago. This consisted of about 15 extramural NCI and DOE funded scientists with expertise in computational and biological domain areas. They met about 2 to 3 times a year, and they were charged with technical evaluation of the JADAX4C pilot projects, as well as ATOM, and exploring additional areas for mutually beneficial NCI and DOE collaborations. The other component that we referred to as the NCI DOE Collaboration Governance Review Committee. This was comprised of about 15 senior federal leadership members and program leads from both agencies, also met about 2 or 3 times a year, and was charged with guidance on strategy, policy, program management, and budget, and communication with the federal government and the executive branch. And then finally, more recently, under FNLAC, there was a task force convened. This consisted of about 12 extramural and intramural scientists with expertise in computational and cancer domain areas. They met periodically between May and October of 2020 and were charged with review and assessment of the merits of the individual projects, evaluation of whether the collaboration should continue and become a more sustainable and stable partnership, and recommendations for future directions. The task force was chaired by Dr. Joe Gray of Oregon Health and Science University, and the final report was delivered at the October 2020 FNLAC meeting. So I'm going to now just give a couple, next slide please, a few more details about what this task force recommended. So overall, the task force saw that the collaboration is uniquely suited to address certain critical challenges in cancer research and should continue. They also noted that the current pilots are really large, full-scale projects and should be evaluated as such, and this includes a reassessment of the level of funding. Furthermore, the future projects should be developed and reviewed by a more structured and rigorous approach, and this includes engaging the broader computational and cancer communities to allow for increased collaboration and leveraging other current NCI investments in systems and computational biology. They also noted that it would be good to increase engagement with NCI extramural communities, and this would be beneficial to more strongly integrate cancer researchers into the projects and increase the relevance to the cancer research community. And finally, they asked that project-specific advisory groups be established, and this would be needed to increase the scientific oversight and engagement. And now, next slide, please. Moving on to the project-specific recommendations. They recommended that pilot one, this was the preclinical predictive modeling for preclinical drug development. This should be concluded based on insufficient available and pertinent data and insufficient integration with NCI investigators doing predictive modeling. Pilot 2 should be continued with a greater focus on refining the coarse grain models based on data from the atomic level simulations and on experimental validation. And pilot 3 should also be continued with a greater focus on implementation and multi-institutional deployment of the developed APIs, as well as expansion beyond NCI's surveillance, epidemiology, and end results, or SEER program for short. So in accord with these recommendations, NCI and DOE entered into talks and decided to sunset pilot 1, and it's currently in the process of being sunset and is just about concluding now through early August. Importantly, all the data that was developed and made AI ML ready will be publicly released. And this includes data from a variety of cell line as well as PDX and human sources. And this is going to be available in a repository that I'll show more of in a few slides. And also the developed models and software will be publicly released. Next slide, please. So this slide shows how we are restructuring the governance and oversight for the collaboration going forward. We are going to do this in 3 components as depicted here. The FACA level oversight is shifting from NCI to DOE's Office of Science. We have agreed that this component is going to follow DOE procedures that are yet to be exactly determined. We will also, as the task force recommended, have scientific and technical advisory committees for each project. These will consist of 4 to 6 scientists per project who have targeted and deep expertise relevant to the assigned project. The pilot leadership, in consultation with federal executive committee, will select the members, and the meetings will probably be approximately quarterly. The charge will be project-specific, in-depth scientific and technical guidance and advisement. And then the final component is what we're referring to as the executive committee. This is comprised of senior federal leadership from both agencies. We actually had our first executive committee meeting earlier this week. For NCI, the members are our director, Dr. Ned Sharpless, as well as our deputy directors, Drs. Doug Lowy and Dina Singer. And for DOE Office of Science, the members are Drs. Binkley and Helland. And for NNSA, the members are Dr. Anderson and Ms. Tuk Wong. The executive committee is charged with interagency strategic partnership status and relationship health, overall funding, program priorities, and implementation of ASCAC recommendations. Next slide, please. Okay, so now I'm going to talk a little bit more specifically about the individual projects or pilots. Pilot 2, as I mentioned, is titled RAS Biology and Membranes. It is co-led by Fred Streitz at Lawrence Livermore National Lab and Dwight Nisley at Frederick National Lab. The overall goal is to deepen the understanding of RAS biology and identify new drugs for RAS-related cancers through an integrated development and use of new simulations, predictive models, and next-generation experimental data. The aims of this pilot are to understand how RAS and RAS complexes are activated, provide new insights into RAS intracellular signaling, and down the line, potentially propose potential new therapies targeting RAS, or maybe RAS effector proteins. The pilot applies multi-scale molecular dynamic simulations of RAS-RAF interactions on a realistic lipid bilayer membranes. A few examples of current capabilities that the pilot has developed include feature reduction of molecular dynamic simulation output using an autoencoder, simulation of curved bilayer membrane surfaces referred to as MEMSurfer, and determination of important samples in a constantly changing data set. Going forward, the team's goal is to elucidate the molecular details leading to activation of an important RAS effector protein called RAF by mutant RAS at the plasma membrane using powerful and unprecedented multi-scale simulations. To achieve this goal, the team will build upon their newly created multi-scale machine-learned modeling infrastructure, or MUMMI for short, to capture biologically relevant time and length scales. This architecture will provide highly accurate simulations that are self-healing, have quantifiable uncertainties, and enable the generation of powerful new and testable hypotheses. So now moving on to pilot 3, which, next slide, please. Thanks. Moving on to pilot 3, which is population information integration analysis and modeling. This is led by Gina Tarasi at Oak Ridge National Lab and Lynn Penberthy at NCI. The goal of this pilot has been to modernize National Cancer Surveillance Program. This is, as I mentioned, the NCI SEER program that represents about 35% of the nation's cancer patients. And the program is actually going to be scaling this up to almost 50% of the cancer patients in the near future. By developing and deploying scalable deep learning solutions. The data that this pilot uses is extensive and contains a wealth of PHI data that comes from 7 SEER cancer registries, including 1 million unique cancer patients and 3.5 million cancer electronic pathology reports. Annotation of data has been key to this pilot, including elements such as cancer site, histology, laterality, behavior, and grade. The methods that the team has employed, I'm sorry, I'm going to first mention the aims. So the pilot, as similar to pilot 2, has 3 aims. The first aim is to automate the way information is captured from reportable cancer surveillance data items in unstructured clinical text to improve the capacity of the NCI SEER program. The second aim is to advance the integration and analysis of extreme scale graphics, visuals, and data management systems to better understand drivers and patterns of cancer outcomes and predict clinical endpoints. And the third aim is to promote data-driven modeling of patient-specific and population-level health trajectories to guide precision cancer care. So the pilot has employed multiple deep learning and natural language processing algorithms to cancer pathology reports, and they are now expanding this to radiology reports. The methods include convolutional neural networks, self-attention networks, and large-scale transformer language models, which the team is just beginning to explore. Uncertainty quantification has also been crucial to this pilot, and the APIs that are delivered to the SEER registries have uncertainty quantification in the form of an abstention classifier built in, which has been absolutely essential for their real world deployment. Also, in terms of deployment, as I mentioned, the deep learning natural language processing APIs that have been deployed to the SEER registries have resulted in significant time savings and workload reduction. And the team is working on deploying to 6 or more registries starting this year. Next slide, please. It's also important to note some of the DOE infrastructure that's been critical to this pilot. As I mentioned, SEER data contains PHI or patient health information that is private and must be protected. So the pilot has used knowledge discovery infrastructure at Oak Ridge. This is a secure PHI enclave with GPU computing resources for data storage and AI model development. They've also used Citadel, which is a privacy-preserving computing solution that enables secure large-scale training and hyperparameter optimization of deep learning models using PHI data on Summit. And then also, they've used ALCC allocations on Summit for some of the work. And then finally, they've also made use of Frontier for optimizing Transformer pipeline on early access hardware. It's also important to note in terms of the exascale mission that delivering general software modules on Summit and Frontier for large scale pre-training of Transformer language models for clinical, biomedical, and other domain science applications. Next slide, please. Okay, now I'm going to talk a little bit about the Improve project, which is just in the process of starting up now. This project is a follow-on to Pilot 1 that demonstrated state-of-the-art performance in deep learning models for drug response prediction, as well as cross-study validation, data and learning scaling, active learning for drug response, multimodal learning, and data quality impacts on model performance. Improve is being led by Rick Stevens at Argonne National Lab, as well as Frederick National Lab and NCI. The exact leadership there is still being determined. And we will also have a competitively selected group of extramural community investigators participating directly. The overall approach is to develop a general computational framework for deep learning model comparison, evaluation, and improvement, and demonstrate progress on this goal in the cancer context, but make the framework available for other DOE projects, such as materials, synthetic biology, climate, etc. The project has 2 coupled goals. First, the development of a robust framework for comparing deep learning cancer drug response models, including creation of evaluation data sets and performance benchmarks, supporting research to improve models and documenting state-of-the-art performance on an annual basis. And second, the design and execution of high throughput experiments aimed at producing new data sets, explicitly aimed at the training and evaluation needs of deep learning cancer drug response research, and working with the community and private sector to carry out the large-scale data generation needed for model improvement. Aim 1 is focused on the development of a deep learning model comparison framework. Models will be developed in the context of generalizability, both in the tumor and drug spaces, and advancing the interpretability, explainability, and fairness of models. NCI intends to fund 3 to 5 extramural model design groups to actively collaborate. It should also be noted that Improve is loosely inspired by the long-standing DOE effort to compare climate model performance supported by BER. Next slide, please. Improve also focuses on designing data generation experiments explicitly aimed at improving deep learning models. And aim 2 is this data generation aim. The overall idea is that the aim 1 modeling and analysis effort will converge on priorities for initial data generation. And once aim 2 data generation groups are in place, data generation and validation can begin, thus starting an overall loop between modeling teams and the data generation teams. The plan would be to execute campaigns approximately 4 times a year. The end result of Improve includes additional innovation in the development of new approaches to drug response modeling and prediction, as well as a reduction in the uncertainty when evaluating potential progress in modeling, when new results are published and certain conclusions or claims are made. Next slide, please. So the last project I'm going to touch on is the public-private partnership I referred to earlier as ATOM. So the current state of drug discovery is that it is mostly linear, sequential, staged approach that balances cost and risk. Millions of molecules are screened each year. Thousands might be made and tested, but most fail. So the overall goal of ATOM has been to accelerate and democratize the drug discovery and optimization. And they're asking, can independent government entities and the private industry work together to attain this goal? They are going to be focusing on small molecule drug discovery and first focusing on cancer target. At the bottom of the slide, you can see that ATOM had 4 founding members starting when the consortium started in October of 2017. These were Frederick National Lab, UCSF, Lawrence Livermore National Lab, and GSK. These organizations formed the consortium through a multi-party CRADA. ATOM has recently transitioned to being a nonprofit organization under a 501c3. Recently, 3 Office of Science labs, Argonne, Brookhaven, and Oak Ridge, began participating. The participation of these labs is limited to CRADAs, and there is no direct Office of Science funding. Now I'd like to talk a little bit about some of the capabilities that have been developed by the collaboration. As I mentioned earlier, one of the main capabilities is referred to as CANDLE, or Cancer Distributed Learning Environment. This is an open source, collaboratively developed software platform providing deep learning methodologies. It's supported by the Exascale Computing Project and led by Rick Stevens at Argonne National Lab. The CANDLE platform enables cancer researchers to access key features at the forefront of data science frontier shaped by advances in deep learning by including features such as hyperparameter optimization to efficiently identify the most effective model implementations and scalable data parallelism to speed machine learning where very large data might be required. It's a scalable system and was originally developed on DOE's leadership class computing, but can be run on much smaller systems, even personal computers as well. And just to point out, there is a implementation of CANDLE available on NIH's supercomputer BioWolf. Next slide, please. More recently, we've also stood up a predictive oncology model and data clearinghouse, or MODAC. This is a data sharing repository developed to transition resources from the labs where they were developed to the broader research community. The resources, as I mentioned, include data sets, software, and models from the computational capabilities developed by the JADAX4C pilots as well as ATOM. Also, there are annotated data sets in MODAC, and it is continuing to expand weekly with new capabilities. Next slide, please. Just very quickly, I also wanted to point out that all of a list of all the developed capabilities as well as publications are available through NCI CBIT's website. The URLs are listed here. And importantly, and I think that something that will be helpful to the community is that they are cross-linked to each other so that the capabilities are referenced to the publications and the publications are referenced back to individual capabilities. The next slide, please. this just is the snapshot of the list of publications. And again, this is being updated weekly. So finally, I'd like to talk about new opportunities that our agencies might have that can be pursued together. So since 2019, NCI and DOE have established what we refer to as the Envisioning Computational Innovations for Cancer Challenges, or ICC community. This is a transdisciplinary community across advanced computing and predictive oncology. We've really used this community as an incubator for potential new areas of collaboration. All ideas that have arisen from the ICC community have been driven by community members and are not coming top down from our agencies. We've fully engaged a wide set of extramural research communities, as I mentioned, from the beginning, and they've been crucial in terms of vetting new areas of research at this intersection of cancer and advanced computing. As you can see here in the boxes, we've had several events and just had another event earlier this week. Some of the events and activities have included an initial scoping meeting that was held in March of 2019 at Lawrence Livermore National Lab. We used this scoping meeting to identify important cancer research challenges that will require AI and advanced computing to move forward. The scoping meeting was attended by over 70 computational cancer challenges, and the community identified 4 main challenge areas, including developing digital twin technologies, adaptive treatments, synthetic data, and machine learning driven hypothesis generation. We further advanced 2 of these areas, especially the cancer patient digital twin and adaptive treatments, more specifically precision radiation oncology, through several more events in 2020 and 2021. In 2020, we held a 5-day intensive interactive ideas lab on developing cancer patient digital twin technologies. The Ideas Lab resulted in 5 seed projects that are currently being co-funded by NCI through Frederick National Lab and DOE's Office of Science for a duration of 6 months. The projects are concluding this summer, and earlier this week, we hosted a joint meeting with awardees from another NCI Innovation Lab on advancing cancer biology through machine learning and mechanistic modeling, so that awardees from both events could interact and potentially form new collaborations to continue their research. It should also be noted that several DOE National Lab scientists from PNNL, Oak Ridge, and Sandia National Lab were part of the funded teams from both events. In addition, earlier this year, we partnered with the DOE and the American Association for Radiation Oncology on a series of workshops aimed at advancing precision radiation oncology through advanced computing and AI. Essential components of this include personalized, adaptive, improved treatment through understanding and development of mechanism-based computationally enabled modeling, and advanced computing to achieve dynamic, multi-scale, data-informed, clinically actionable predictions and decision-making. Both agencies felt that the workshops were very successful, and we are currently finishing a comprehensive report that will be a resource to the community. We're also discussing with DOE's low-dose radiation research program and NCI's radiation oncology biology integration network potential ideas for joint projects. If you're interested in learning more about any of these community events or activities, the bottom left square has a link to our online platform. We use the NCI hub site. And so I would encourage anyone who is interested to please take a look at that site, and also happy to answer any questions through email. So with that, I will finish up and happy to take any questions or comments.
Thank you, Emily. Jill.
Well, first, I want to thank you, Emily, for this very comprehensive presentation. I've been looking forward to this sort of since this meeting began. I was looking forward to your talk because, in fact, I was a member of FINLAC when this idea was first presented.
Yeah.
And so it's been very interesting to me to see the evolution of this idea. I have to say that, well, I have many things to say, but I don't want to speak as long as you did. But first of all, I was happy to see that all of these pilot projects were looked at quite seriously. I will say that when Pilot 1 was first presented, many of us were dubious in terms of availability of data, and that turned out to, in fact, be an issue. And so I was glad to see that Joe and his committee decided that was probably one that should be, and in fact, it's really kind of being reformulated through this improve project that you describe. I think there are still going to be challenges with improve because cancer data is very complex, it's very heterogeneous, it's very context dependent. Biology is not, what is the word I am looking for? It's incredibly stochastic. I mean, it's just not so easily predictive. And this problem of drug response prediction, that some of us call that patient stratification, this is something that the computational biology community within the NCI has been working on for many, many years. And one thing I'm pleased to see is this effort now to engage more of the NCI extramural community in the work of this collaboration, because I think that was really missing at the beginning. And I think that there is an incredible breadth and depth of expertise, experience, knowledge, and useful tools that have already been created. A lot of work that's been done targeted at every one of these challenges that you described. And so I do hope that in this NCI DOE collaboration, more and more of that extramural NCI community begins to be engaged to also help cross-train the people in DOE, which I think is critical to making really substantial progress on these problems, which are just very, very hard problems. I was interested to hear about the natural language processing issue that you raised, because, man, that data is very dirty. And if you look at medical records, they are a mess. And to try and extract meaningful data that you can plug into a predictive model, that is no easy task. And it is something that the community, the NCI community, and the computational biology community at large has been looking at and working on for many, many years. And there's a lot of experience and knowledge there that could be gained by sort of opening up to the community more at large.
I didn't have, Jill, I didn't have time to go into all the details, but Pilot 3, they have many collaborators in academia. I can provide a list. Yeah.
I think that's great because it's a really, really hard problem. And if you go to every cancer center around the country, you'll find that we're all dealing with that problem. And because we want to make use of our own patient data, and how can we do that given the way Epic is a help, you know, electronic medical records are a help, but they're not the end goal, right? They don't solve the problem.
They
so
also, I just mentioned really quickly, sorry, that that team is also in the process of developing what they're referring to as privacy preserving APIs that will protect the PHI data that's used to build the algorithms. And so they're starting to now be able to collaborate with outside entities such as CDC and VA with those algorithms that protect the data.
No, that's great. And you also want to set up trusted brokers so that that the right people are getting access or not. And I'm sure Sue also is aware of this, that there are many databases that NIH has been funding for a long time, where there are trusted brokers that not everybody can get the data. You have to say what you're going to use it for, and so on and so forth. But mostly what I'm very, very excited about is the idea of opening up this collaboration more to the outside and to the community, to the NCI community, to the NIH community at large, because I think it's going to make it such a much more powerful thing. And I really look forward to talking to you guys more about this. As I said, I could now talk for, a half an hour, but I'm not going to. I'm going to spare you all that. But it's really exciting to see how the programs develop. And I look forward to a lot of success leveraging all three: NCI, DOE, external, NCI research community. And really, we've got a tough row to hoe, as they say, to attack this disease. Really do.
Thank you.
Thanks, Emily. Great work.
Thanks, Joe. Ben?
Hi, it's Vin. I just noticed on one of the slides, it looked like you were using the digital object identifiers to associate with something. I didn't know whether it was the genetic string or some other thing. What was that all about? It was probably 2 slides back from the end.
Well, I know we have our, this is not going to be what you're asking about. I mean, certainly the publications have DOIs, but that's not what you're probably.
No, well, that's why I was asking, because it looked like the DOIs were being associated with some piece of, DOI is just a digital reference for a digital object. Could be anything that's digitizable. It doesn't have to
we do. So, okay, I'm looking back at the slides. Yes, so it does appear that I think you're talking about
the global identifier for asset. So what's an asset?
Oh, there we go. So the assets are we're just using different terms. The capabilities are our assets. Sorry for switching terms. So the model. So we've been giving individual DOIs to the individual computational models that have been developed.
Okay, that's fascinating. Because in a way that says that the DOI is potentially executable, which is pretty interesting. Okay, thank you.
All right, thanks, Finn. Other questions for Emily? I'm just watching the hands up here. All right, going once, twice. All right, so thank you, Emily, for that overview. Really appreciate it. And it's a good setup for talking about the new charge, because it's related to this interaction. So Barb, over to you.
Yes, can you see my screen? Hopefully it's got the charge.
Yes, we can.
Yeah.
All right. So Dan on Tuesday received a letter from Dr. Binkley, thanking him for his work as a committee chair, but asking, noting that the Office of Science and National Nuclear Security Administration began collaborating with the National Cancer Institute in 2016 to dramatically accelerate the progress of cancer research to the application of high-performance computing and artificial intelligence. The collaboration through the Memorandum of Understanding is called the Joint Design of Advanced Computing Solution for Cancer, JADAX4C, and as we noted earlier today, has been renewed for an additional 5-year period. The letter notes that ASCAC generally provides advice and recommendations concerning the Advanced Scientific Computing Program in response only to charges from the Director of the Office of Science. However, the committee's objectives and scope of activities include periodic reviews of elements of the Advanced Scientific Computing Research Program and recommendations based thereon. And considering this, Dr. Binkley has requested that ASCAC form a working group to review the activities under this collaboration and to provide advice to the Office of Science regarding new opportunities that might contribute significantly to these efforts to identify any major challenges that are preventing the efforts from delivering their potential and to provide recommendations for how the Office of Science might address these challenges. He's further requesting ASCAC to establish a working group for the life of the collaboration or until this charge is withdrawn. The working group should report findings through ASCAC in an open public meeting or video conference meeting of ASCAC as needed, but at least annually, to identify significant opportunities and challenges in a timely manner. The ASCAC chair will transmit the working group's finding in the form of a letter report to the director of the Office of Science after the letter report is accepted by the full committee in an open public meeting. If you have any questions, please contact Christine Chalk. And as you can see, there's Steve's signature and his appreciation for your willingness to accept this charge. With that, I will stop sharing and just note again, thanking Emily for leading us into this discussion. And as she noted, and as I noted in my talk, that we will be taking over the review of the projects of the NCI, of the progress of JDAC. Now, I do want to make a note that Adam is now a nonprofit, so Adam is not considered as part of this. It's only the three, Project 2, Project 3, and now the new improved project that are under the scope of this charge. I want to thank Tony Hay for agreeing to lead this new working group. And I also want to thank Martin Berzines, who actually served on the previous NCI review process. And so I just want to note that Christine Chalk actually, in addition to her other duties, assumed responsibility for this, for the NCI and JDAC's FERCI partnership when Carolyn was on left. And so I'll turn it over to her if she wants to add anything.
Thank you. No, you thanked everyone for me, so I think we're good. We will be forming this working group to do a high level evaluation. Each of the projects, as Emily mentioned, is going to be forming their own scientific steering committee to give them really detailed insights into how they could improve the collaboration. But this working group, we're hoping, will help us just keep an eye on whether or not they're making progress, delivering on their milestones, posting things into the MODAC, and that sort of a thing. So I thank Tony. I appreciate that you were willing to do it. I hope you're still willing to do it. And we'll get started on the new chart.
And we'll be reaching out and asking for participation. So if you're interested, let us know. Any questions about this? All right, Satoshi is going to tell us about the Summer Olympics. No, wait, that's not right. Satoshi, are you here?
Yeah.
There you are.
Well, yeah, we're doing good as a host country. Obviously, U.S. is probably the most prominent athlete country in the world. I think also China, we're seeing sort of a three-way competition with medals. Yes, doing very good. Yes. Oh, that's not the subject matter, I guess. Okay. So thank you. I'm Satoshi. I'm director of Beacon RCCS, and DOE and MEXT, our Ministry of Education, Sports, Culture, Science and Technology, had been in significant collaboration, and we have been leading a charge. And it's my pleasure to be able to present to you some of the updates regarding Fugaku, but also give you a little background for those of you who are interested but have not had the opportunity to learn the system. But I'll keep that short in the interest of time, and give you more of a update. Try to give you more of an update as to where we are and where we will be. And okay. So So initially, Fugaku, just to give you a background, initially Fugaku started as a project to build the next generation exascale machine after the K computer. But you know, when we went back and thought, well, what do we mean by exascale? Is it about exaflop, achieving FP64 exaflop and peak or LIMPAC? Probably not. Of course, there were lots of difficulties we foresaw because our time frame was like somewhere around 2020, and would have been very difficult to create a machine achieving that. And of course, there are some questionable metrics with regard to scientific validity of achieving that. Any floating point precision being 1 exaflop, there are some validity to that. And of course, in HPLAI, had reached 2 exaflop in mixed precision. We're not the first to reach that. Summit actually, for example, Gordon Bell 28, the winning application had to achieve 2 exaflop as well. So in some sense, we are already in the exaflop arena, exascale arena from that perspective. But what was most important was to get application performance, being sort of application first philosophy. And the real objective that had been set was to achieve somewhere around the neighborhood of 2 orders of magnitude increase in application performance for real applications that were important to us and also to the world, compared to the machine circa 2011, 2012 timeframe, you know, K computer and machines in the US and so forth. And so that was set to be the real project objective. And of course, we had reached that, as I'll tell you later. The average speed up for the target application had been about 70x compared to the K. Of course, this was not without difficulties. Of course, we had predicted what if we go off the shelf, you know, buy commodity processors circa 2019, 2020 timeframe and try to build a machine. And it was deemed fairly difficult. Of course, we could have gone a more specialized, we could have built a more specific, specialized machine, but then programmability would have been difficult, especially for the Japanese scientists who are less adept to work on these heterogeneous machines. So we had to build a general purpose machine built based on general purpose CPU instruction sets. So the only solution, of course, was to build our own processor, which we, of course, had the ability to, but of course was not without difficulties. So in essence, it was a moonshot project because the bar we had set was really high, especially with respect to power efficiency. We had to achieve somewhere like 3 times power efficiency compared to the available power efficiency that could be achieved by Xeons and other types of off-the-shelf processors with general purpose CPUs. And of course had to perform well and had to be general purpose. So that's why we adopted ARM as the instruction set and work with ARM and other companies, in particular like Cray, to establish the scalable vector extension. So, but of course this was achieved with considerable co-design activity because even as early as the late 2008, 2009 timeframe, just about the time when the DARPA report came out for exascale, co-design was stressed as the most important means of achieving exascale. And of course, we followed that this week. So we, essentially the entire Japanese HPC community had gathered to establish the co-design working framework under RIKEN, and of course with partners with Fujitsu. But it was really the entire application community and also significant participation from the computer science community to conduct this co-design. So we had set 9 target applications, and most of these, there's a little bit of basic science, but most of the application areas were pertinent to what we now call SDGs, or Sustainable Development Goals, like health, medicine, environmental disaster, energy, materials, and so forth. And the objective was to establish about 2 orders of magnitude speed up, and for some of the applications, actually achieve over 2 orders of magnitude. And as you can see, for drug discovery and for environmental predictions, we had achieved about more than 2 orders of magnitude speed up. But if you look at the overall average, you see that the achievement of speed up achieved over the K computer is well over double digits, approaching 2 orders of magnitude. So this chip, I'm sure you've seen these in various talks and press releases, so I'll be very brief. So it's the first general purpose processor to server class processor to use 7-nanometer process. And of course, the microarchitecture is our own, although we comply with all the ARM standards. And it's the first general purpose processor to use HBM2. So for GPUs had used HBM2 in the past, especially, for example, Pascal and Volta and so forth, but this is the first. And I think it still is the only general purpose processor to use HBM2 on-die integration. So the modest, so the flops performance is fairly modest, but that's because, we found that most of the target applications are memory bandwidth bound. And thus the priority was to basically establish much higher bandwidth as compared to what's afforded by conventional DRAM technologies like DDR4. So we got all equivalent bandwidth that's compared to, let's say, a state-of-the-art GPUs, about 1 terabyte per second in catalog, and about 0.8 terabytes per second in terms of real measured bandwidth stream, like something like stream triad. So a lot of attention, a lot of people pay attention to the processor performance and power efficiency, but a lot of effort also went into making the interconnect and other peripherals low power and also high performance and highly functional. So it's probably the first server CPU to integrate the interconnect onto the die. So we have a Tofu D, which is the evolution of the Tofu network that was used for K, but of course much sped up. But not only sped up, but entirely not only the network interface, but also the the network switches, entirely integrated the die. So so actually Blue Gene did this, but it was a much more specialized processor. So you can argue whether Blue Gene Q was the first to do this, or Fugaku was first to do this. But this is, but the performance level and the fact that this is a general purpose, much more general purpose processor than a Blue Gene Q processor, I think still warrants the fact that this is the first chip to do this, in at least my opinion. So not only Fugaku has 160,000 nodes, but also has 160,000 switches, and since each switch has 10 ports because it's 6-dimensional torus, has 1.6 million network ports. So it's a massive network machine. And also we made it so that in order to mostly speed up MPI to reduce the CPU overhead and also reduce the latency, we essentially, Fugaku is the disaggregated architecture in terms of being able, any processor in the system being able to access any memory in a system using a very fast RDMA without the CPU intervention. I'll be very fast. If you have any questions, you can feel free to ask me later. So in some sense, Fugaku CPU is a combination of a standard, a fairly capable CPU, not as capable in integer compared to, let's say, the latest Intel, which is much faster in integer. And but in terms of HPC workloads, which are more bandwidth or latency dominant, it performs very well. But so the core is is weaker compared to, let's say, something like a Skylake or Cascade Lake, much stronger than, let's say, Xeon Phi cores. But much like Xeon Phi, there's lots of bandwidth features, or much like GPUs, it has it's a streaming architecture also as well. And there are not only memory, but has features to accelerate memory bandwidth, and also things like collective operations. And also there are like GPUs like GPU functions like being able to do scatter, gather, strided access, coalesced memory access, and so forth. A lot of which also comes from heritage of Fujitsu as a vector computing company. So what was most important was the power efficiency, not so much just the absolute speed, because facility-wise, in order to achieve the speed up measures we were anticipating, as opposed to the available power delivery ability of the data center, as well as the cost metric, we had to be about 3 times more efficient, as I said. And we had achieved that. So the left-hand side, you see the familiar faces in terms of most of the major open source software. When tuned properly, they achieve about 3 times power efficiency if you line up the same number of cores as opposed to Skylake or Cascade Lake in the latest incarnation. I don't know if they've done comparison with Ice Lake. So so that means the flip side of this, had we built this out of, let's say, a Cascade Lake or Ice Lake, then we would have had a machine that would use like 100 megawatts, so which would have been impossible to basically foster, both in terms of capacity but also in terms of cost and capex and opex costs. So like I said, the Tofu D interconnect is integrated into the die. It occupies about 25 millimeters of die area, about 6%. The entire die area of the chip itself is not that big. It's about a little less than 5 square millimeters. And power is really low. So that's one of the reasons with the die integration. It's about 8 to 9 watts, including a SerDes and AOC. And some of you are familiar with the computer architecture. The hard may argue that, well, if you had just a single AOC, this may consume like 10 watts. Well, the secret here is that the single AOC is shared by 2 chips. So we have the power requirements. So the actual interconnect switching fabric, as opposed to SerDes, is really, really low. But still get 400 gigabits per second bandwidth out of the chip, scaling to 160,000 nodes. So it's a very scalable interconnect, low power, and that was the intent. And like I said, there are direct DMAC access to L2 cache. We can do cache injection. We can do any sort of RDMA access to any memory segment in any system, any parts of the system. And we have 160,000 of these network embedded. So there are no external network switches other than those for I/O, for which we do use InfiniBand. So end-to-end latency for the best case is about 0.5 microseconds, and we get about 40 gigabytes per second, nearly 40 gigabytes per second, which is about 93% efficiency compared to the wire speed for MPI. So it's the memory bandwidth. It's not only memory bandwidth, but also the network bandwidth is quite good. Although it's quite a step down from the K computer, which was basically over provisioned in terms of its network bandwidth. So like I said, so this is the architectural slide. And we have, although we may compare it to Xeon Phi, the internal the core-to-core interconnect is totally different, so we use crossbar to constitute what's called a core memory group. So there's one of the problems Xeon Phi was the bandwidth and also latency between the cores was very poor. But this is not the case for this chip, and also the L2 cache is also directly connected by crossbar to all the cores. And because of the DMA controller, there are plenty of DMA controllers that are directly attached to network on chip, and the network is parallel to the PCIe. So it's not a I/O connected network. The network is directly embedded into the die, very much like NVLink and GPUs, but also with the network ports, scalable network switches. So you can get. But down below, you see how you may be able to access any parts of memory through the fabric onto the L2 cache of any core, any die in the system. So like I said, it's 160,000 nodes, and there are varying flops depending on the precision, but most importantly, we get about 163 petabytes of bandwidth for the entire system for the memory bandwidth, or the measured bandwidth was about 120 some petabytes per second, which gives us about 3 petaflops per for this HPCG. So it's a fairly balanced system as opposed to systems like those are from like China, which are designed to win the Limpac war and not on real applications. And so being based on standard ARM-based cores, there's a huge discussion with regards to how we may integrate the modern software stack with the traditional HPC stack. Well, so this was achieved fairly transparently, being based on standard software stack, standard ISA, and also everything else being like server specifications and so forth. So Fugaku actually accommodates all of the familiar HPC software stack, and in addition, all the familiar cloud software stack runs naturally in production on the system. The only thing we really had to develop intensively was the deep learning software stack, which has its own special optimization, requires some special optimization, and the ARM portion was not there. So we had to take the Intel 1DNN and create an ARM version of it to make deep learning excel on Fugaku. And also work with DOE, especially with the SPAC team, to allow for package management of all these software stack, which is very complicated. So we work with the open source community on trying to get all this optimized software stack on top of ARM plus SVE. Also, all the cloud features are implemented by default. Any user can use those cloud features, but we also are working with the companies within Japan, also from the US and so forth, to have Fugaku serve as basically the cloud backend, so that these companies can't put their specific cloud services on top, so that the companies, especially those from industries, can access Fugaku and utilize these high-level services. And I also already talked about deep learning software stack. So the efficiency of H4FX with respect to FP16 is really good. Although the GPUs have improved dramatically in the last edition of HPLI, although it's still in the 30–40% range. But on the other hand, some A100 sports a significant per chip performance. So if you compare chip to chip, of course, A100 really excels. But still, it's a little bit of mystery why they cannot get much higher percentage efficiency. But nonetheless, the software one advantage of NVIDIA and respectively, they pour tremendous amounts of human resources into perfecting their software stack for AI and deep learning. And they have to really praise for making all that effort. So so we have set it out doing our own stuff. It's Weekend and ARM and other affiliate companies. So now we have a fairly decent software stack. I won't go into details of implementation. Actually, it was a huge challenge to do this, but now we have a very respectable, fairly respectable performance that allow us to get #1 for general purpose CPUs machine and MLPerf newly established MLPerf HPC benchmark. So Fugaku is now in production, and about 40% of Fugaku, of course, under normal production is chopped up into various programs. About 35 to 40% is dedicated to these very special programs, which are called priority areas, which are outgrowth to priority areas, called research promotion program. And if you look at all the topics, they cover a lot of the SDG type of high-end applications that are outgrowth of the co-design process. Co-design. I won't go into the details of each one, but you can read what the topics are later in the slides. But they cover energy and environment, drug design, medical, and so forth. Considerable collaboration with DOE labs, and we opened up the machine to the coding team, DOE coding teams, thanks to Doug Cothey and Took and other people who have really helped in this effort. Mike Carew, Lori, all our friends, and of course there is still mixed results because the ARM HPC ecosystem, especially at the compiler level for this SVE, is still a mixed bag. So for the application that can exploit the capabilities of ASCAC fully, they get tremendous performance. They get sort of a similar performance to GPUs on a per chip basis, or especially with CFD apps, type apps. Now, for some of the cases when compiler fails to vectorize, it's a familiar story. We get very poor performance, but that's something we knew what would happen, and it's all part of creating these ecosystems jointly, because NVIDIA has maybe buying ARM. We don't know what the final story will be, but if irrespective of the outcome, ARM SVE hopefully will be an ecosystem, HPC ecosystem to stay, and then we attaining optimal performance out of the ARM SVE ecosystem will be very important globally. So it's a very conjoined effort. A few words about COVID. Very good talk earlier. We're doing very similar things with Fugaku and other supercomputers, but in particular, we released a whole full power of Fugaku. Well, not full, maybe about 20–30%, but we allocated to the COVID major COVID programs, all the way from molecular orbital calculations, especially with the new strains, how the precise mechanism of their stronger bondings compared to traditional strains, from pharmaceutical investigations, comprehensive docking work to identify new drugs like drug repositioning, to more societal epidemiological work. For example, what's the impact of lockdown, economic impact of lockdowns. And but probably the most famous and probably the most prominent was the aerosol simulation, which was really effective. So, we were really disturbed when WHO announced that masks, early on, if you remember, masks as not being effective. So, the recommendation was not to wear masks, which is somewhat misinterpreted, but that was a message which really disturbed us. So, but when we talked to a lot of the experts, they said, well, there are lots of medical evidence that's lacking with respect to the effectiveness of masks, and the simulation, precise simulations, not so much the coarse-grained rough simulations, but precise simulations were so very lacking, or experiments there, and experiments were very difficult. So what happened was there was a team doing simulations on manufacturing, especially automotives, and also engines, especially fuel injectors and combustion simulations. And they suddenly realized that fuel injections, the physics of fuel injectors, and someone coughing and spewing virus-ridden aerosols, and the aerosols traversing through the air and evaporating, the droplets traveling through the air, evaporating to become aerosols, sticking to the walls and, or face shields and penetrating through masks and so forth. Is essentially the same physics. So which was very complicated to simulate with the engines, but they could take the same technology, work with the experts in virus infection, and then come up with a very precise model of these types of droplets never done before. So if you look at these animations in detail, you can see, for example, the droplets are colored by their sizes. Of course, you see that the face shields are very effective, and also our masks, but we model the masks precisely, even how they inflate under pressure from, when someone coughs. And then you can also see that droplets, as they travel, they change color, and that means as they travel through the air, they evaporate. Some turn into aerosols, which stagnate in the air for a long time. So that's sort of like it's a very difficult simulation to do. You can apply the same sort of simulation to detect what would happen when aerosols are absorbed by human bodies under mass and non-mass situations. What's scary here is the fact that a lot of the aerosols, even under no mass situation, the larger droplets are captured in the nasals. But if you look at the bottom, I don't know if it's showing on the animation here. But if you look at the bottom here, you see this bottom portion right at the entry of your lung turning blue, which means that these micro aerosol droplets actually do penetrate. In fact, they penetrate about the same, well, not at the same level, maybe about 1/3, but even with unwoven masks, which are pretty effective, they do penetrate and enter into your lungs. So we've done many types of, using the power, we collaborate with the government agencies, industry, including like Boeing, by the way, which is not listed here, Japan Airlines, trucking companies, automotive companies, train companies, building companies, aircon companies like Daikin, and also many institutions to basically create digital twins of societal situations very rapidly. And this is very difficult because if you know, again, these precise CFD simulations, we have the bodies, which are very difficult to create a mesh generation of. And if you take like an automotive simulation, mesh generation of precise details at the millimeter scale, a sub-millimeter scale, it takes 2 weeks just to generate the mesh. But we have methodologies to do mesh generation about 5 minutes. So that allows us to create humongous numbers of digital twins that allowed us to create, replicate precise societal digital twins, and then assess the situation. And we also extended our model so that not only we count the number of droplets, but also have some epidemiological, based on some epidemiological work, try to assess the possibility of infection given the amount of droplets spewed versus how much is inhaled and so forth. So this is a more recent work where you have a bar or something like a small restaurant. And then this is a situation we have no tables, no partitions, and have a fairly normal, but not great ventilation. And this is when you have one infected person sitting in one of the positions here, and what will be the possibility of transmission to any other person sitting there who are non-infected, but what's the possibility of transmission? So if you average out and get this statistical average, it says that if you have one person under this situation, you get about 2% risk of transmission, which may seem small, but when you consider there are thousands of restaurants, and the fact that when you have high infection rates in society, you may have more than one person infected. It'll create a very very serious case of societal outbreak. Whereas if you turn on the ventilation to be much stronger, if you put partitions like some of the restaurants are now doing, and we, by the way, we simulate every droplet, in this case, not just standard CFD, but this is multi-physics simulation. This reduces the possibility to about 0.5%, which is improvement. I'm sorry for the Japanese, I didn't have time to translate. And this is not, these slides are not in your deck. I'll put the deck in the slides later. This reduces to about 1/5. So, and then there are other cases where you can even reduce the risk further. And these types of findings are communicated directly to the government committees, and also not only to the industry, but the government committees that are in charge of preventing the spread of the coronavirus, and instituted as governmental policies for preventing infection. And in fact, our own Prime Minister Suga, he also announced on TV that the people should be wearing masks during dining as much as possible because its effectiveness has been proven by Fugaku simulation. So we getting significant support from the administration and the entire entire Japanese politics. And I'll skip over these. And we're moving forward with creating these digital twins for the various societal situations for SDGs. And that's one of our main studies we have today. And I'll skip over some of these slides. But what about the future? So now that Fugaku is done, I'll spend the last few minutes talking about futures. Of course, we continue with our current work, utilize Fugaku to improve the society, advance our simulation capabilities, not only with the first principle simulations, but also with AI and big data, much as what DOE is doing in partnership with many of the labs here, labs in the US. But also we are also very interested in how these will converge, because otherwise we will not be able to design the next generation system appropriately, or create the next generation, or think about the next generation algorithms, or what will be computer science required to drive these types of simulations. And also we need to broaden our scope to the edge, because it's all about, because we foresee convergence of HPC with clouds and the edge. And in order to do that, we need to advance those areas. Also, we also need to utilize our current generation supercomputers in order to advance the next generation of innovations, including quantum and so forth, and neuromorphic and so forth, using the current generation or next generation machines, because of course the real quantum machines are still, a few decades away. So, so the center, my center in particular, but also there are of course other institutions, but my center in particular, we have people in both in computer science and all high in computer science, and also various, but basically representatives from each of the application domains. We also assimilated a pharmaceutical. We have a new HP AI-driven drug development platform division, and so we have about 20. We're approaching 30 teams to work on, and all these teams collaborate within the center and also with outside to advance this, not only advance state of the art, but really work on, for example, so what's the true story here with respect to convergence of first principle based simulation, empirical AI based prediction, and big data? Because there are lots of ad hoc attempts at doing this, for example, replacing surrogates, AI surrogates with for PD solver. But what's the real story here? What's the government mathematics? What's the theory? It relates to a certain quantification type of work, but we really need to get the theoretical underpinnings applied to real applications, with which only under which we can develop the next generation machines and also the software. So working on that, working to scale deep learning to 100,000 nodes on Fugaku, and these are backed by work for surrogates and also in various areas like from automotives to drug designs and so forth. Finally, what to do next so given this, we're thinking really about the next machine. So we have already written the first draft of white paper about what would happen what would happen if we took the off-the-shelf components circa 2028, when we expect Fugaku to finish its operational status, 2020-29 timeframe. And of course, the outlook is very bleak, because we all know that the Moore's law is ending. So, so of course, we have to do something different. But and we all like to think about this revolutionary change in computing. And we have all these cool technologies on the horizon, how we use them. But we also must remember that these things, anything like heterogeneity or any of the technologies, are means to the end. And when you talk to any of the application people, they're what they say is, well, don't change my code, just make it faster. Of course, that's a very classic attitude. And of course, we don't want that. We want the code design. But there's some truth to it, as much as, for example, we say heterogeneity, but heterogeneity is means to an end. So, in fact, heterogeneity may be evil, right? When we consider that people have to change codes. So we really have to think about the algorithms for the first principles, because not only the algorithms in the current state, but how do they evolve? How will the algorithms themselves evolve to exploit the the parameters in the system that we can improve over time, at least for the next 1 or 2 generations of machines. And one of the things, of course, is data movement, because that's where the most energy is being spent nowadays. But we all know that flops will stagnate because the transistor will no longer shrink and their power will be constant. Whereas there are lots of opportunities like 3D integration and so forth, and new devices, and new memory devices, and so forth, where we may see dramatic opportunities in terms of reducing energy to computation. So, but the only way to exploit that is to change our algorithms to the extent that they become low order algorithm, not the high order algorithms. So going from n squared and cubic to something like n order n, order constant, order root, square root n, order n, and log n. But then there are some algorithms which may or may not be subject to this, but we see this as having very small fraction of the applications. But some are fundamentally hard, like MP. Some are MP hard problems. But this is where the regime where we think quantum computers will be useful. So we can just establish a quantum computing center in collaboration with them, but not to say that quantum computer will take over the world, but to say in what regime, considering this algorithm development, that quantum computers will be useful, and something like neuromorphic computers will be useful, or may not be, because there are lots of practical problems that can be used using conventional computers by slight problem relaxation to get results that are almost as good enough for real applications, and in which we can greatly reduce the algorithm complexity. So we're looking into those areas considerably for the next generation. And also the architectural, what kind of architecture we can build in order to dramatically reduce the data movement. These are fairly classic ideas like, new memory processing and so forth, but we have more of a holistic view on combining with the algorithms how much speed up we will be able to obtain by this algorithmic co-design that we will be conducting over the next few years, and to see what kind of machine we can build. Okay, so that's it, and I'll be happy to take any questions.
Thanks, Satoshi. Any questions for him? We're running a little late, not to any fault of Satoshi's, but we are a little short on time. So questions?
It's Vint. Actually, I have a million questions, but the most important one just got answered in the chat. That's how to get a hold of Satoshi offline. So watch for incoming email.
Okay.
Thank you.
Yes.
All right. Any other questions for Satoshi?
Dan, I just wanted to thank Satoshi for doing this talk for us. That it's so early for him in Japan, and I very much appreciate him joining us.
Well, yeah, and in return, I really appreciate the all the collaboration we have with DOE. We're the labs, especially the coding teams, have been really diligent trying to get the codes running on our architecture, and of course, we expect many of our scientists hopefully will get time on like Frontier, the latest latest machines, and collectively we can share the results, and also of course the science itself to reach new heights. So I think this collaboration between US and Japan are really working well, and so really appreciate this.
And I have to say that pre-COVID, Satoshi may be the only person I can think of who has more air miles than Jack Ungaro. So Tony, your hand is up.
Tony.
Yeah, just a quick one. I have some concerns about ARMS being purchased by NVIDIA, because ARM's business model is not to belong to a silicon manufacturer and a chip manufacturer. And so I wondered, how would this have been possible if NVIDIA had owned ARM?
Yeah, well, that's something difficult to answer. I mean, there are pros and cons, always pros and cons, because I think it may even because NVIDIA is not only a chip company, it's a high performance chip company. So it may compel ARM to have a stronger interest in these in the arena we're interested in. Although of course convergence with edge is important, but invest more into the high performance arena, which may benefit HPC overall. But of course, yes, concerns with respect to dominance and essential hegemony of processor architectures concentrated on a few companies may also be a concern. So, but yeah, it's a mixed thing, and it's very difficult to answer. But we're willing to work with all interested parties, because now, as I said, the borders are especially between U.S. and Japan, along with UK, the friendliest countries in the world, allies in the world, and it's at least for us, it will not be a hindrance to work with NVIDIA, ARM, even purchased by NVIDIA.
All right, Eric.
Yeah, I'm not going to touch the previous question.
Obviously.
But I wanted to ask Satoshi if he could say anything more about potential for expanding the collaboration with the US, in particular around sort of that continuum of connecting edge computing and smarter cities to supercomputing in the future.
Oh yeah, I didn't have time to mention this in the interest of time, but so notice that the digital twin and smart cities team we are instituting in our center, and this Society 5.0 obviously has a huge huge interest in connecting to the edge. So we are already talking to for example, lots of carrier companies like in Japan, it's like NTT, SoftBank, and so forth. And they're very, very interested in being able to, for example, emulate the entire smart city within Fugaku, and not just the environment, not just the physics, for example, in the buildings, the earthquakes, and the traffic, and so forth, but also on the IT. What we're saying is we should also need to emulate the IT portions, because these smart cities will have hundreds of thousands or even millions of sensors, and we need to emulate those components as well. And one advantage of being ARM, to make Eric happy, is the fact that we can directly emulate, for example, let's say a Arduino chip embedded directly using virtual machines, because because we have 160,000 nodes, we can run hundreds of thousands of virtual machine instances and run ARM code directly on them. So so that's a possibility we are seeking, and yeah, and but we're very welcome to collaboration again with our friends at DOE with respect to these kinds of efforts as well.
Satoshi, thank you again, and I was going to say thank you as well, given that time zones. I appreciate it. So I want to, recognizing that we're at our allotted time, I do want though to see if there are any comments from non-ASCAC members before we adjourn today.
And I did have someone ask me public comment, but I don't see him in the participant list. So I'm just going to ask, in case he's on a phone, if Dr. Lowy is on with us and had public comments to make. Give him a minute to unmute if he is on a phone. Okay, I think we must have missed him. So I didn't have anyone else who requested to make public comments. But anyone else who's in the public, this is your chance.
Going once, twice. All right. Listen, folks, there's a lot happening in the world on both the software, the architecture, and the applications front. And one of the things that recent events have made really relevant, and it is how central computing is to every aspect of our lives. Not that we didn't know that before, but it's been brought home in some new ways. So just thank you for today. And Barb, do you have any parting comments?
No, I want to thank you, Dan, and all of the ASCAC members. I think most of us stayed on. And I think it was, I appreciate everybody's comment. And just want to thank you all and wish you a good evening or morning, wherever you are.
And
Christine has something.
Our next meeting will be September 29 and 30. We do have a quorum for those dates. So make sure you have that on your calendars.
And someday we will meet in
We'll
person.
be in.
All right. Thank you all. Have a great rest of your day wherever you are.
Yeah. Yeah.
Thank you.
Bye all.